Hello, where curiosity takes its time and science unfolds in a way that lets the mind wander without hurry. Tonight, we're not talking about the hours or minutes of our own clocks, but about an age so vast and strange that even the word ancient feels too young to capture it. We're going to drift back into the Mesozoic, a time when the world wore a face unrecognizable to us, when life was rearranging itself into creatures that now stand as the most famous icons of prehistory. Dinosaurs were only one piece of it, though they tend to steal the show. There were oceans teeming with reptilian hunters, skies filled with wings unlike any bird we know today, forests that would feel like stepping into another planet, and climates that shaped the rise and fall of entire worlds long before we ever arrived to ask what it was like. Before we begin, I wonder where you're listening from right now. Is it night where you are, with the world settling into quiet, or is it morning and the day just beginning to unfold? It's a curious thing, isn't it, that here we sit in our own present moment while trying to imagine one that lies hundreds of millions of years behind us. If you find this slow journey soothing, maybe give it a like, or even subscribe, if you'd like to share in more of these calm explorations. It helps others find their way here, to this little corner of Earth, where science is less about racing to answers, and more about gently looking around at the wonders we almost forgot. So, let's take that step together, not in a rush, but with the same patience the Earth itself seems to keep. Because if we want to picture the Mesozoic, we first need to let go of what we know today. Close your eyes if you'd like, and try to imagine the world not as it is now, but as it once was. There were no continents arranged like the ones on your maps. North America, South America, Africa, Europe, Asia. They weren't standing in their familiar spots. Instead, they were joined into a giant landmass called Pangaea. At least in the beginning, the land stretched across much of the globe in one continuous sweep. And the oceans were vast, in ways hard to picture. The air would have smelled different, the plants themselves exhaling chemicals into a sky with a very different balance of oxygen and carbon dioxide. Volcanoes were more active in many regions, shaping the atmosphere with their constant outbursts, while strange conifer forests crept across landscapes where mammals, still tiny and quiet, scurried in the shadows. If you were standing there, you might not even recognize the soundscape. No birdsong like you know it. No buzzing of bees, because flowers hadn't yet made their grand entrance. Instead, the calls of early reptiles, the crash of surf against unfamiliar coastlines, and the rustle of cycads in the wind. It was an Earth on the rebound. Just before the Mesozoic began, the world had been through one of its darkest hours, a mass extinction so severe that it nearly erased life. Fall together. That disaster at the end of the Permian period wiped out perhaps 90% of species in the oceans, and a huge portion on land. The Earth was left almost emptied, and the Mesozoic was the slow rebuilding project that followed. When you think about that, it gives the whole era a different flavor. It wasn't just a random chapter of strange beasts. It was life experimenting again after catastrophe, trying new shapes, filling new roles, and discovering possibilities that had never been tried before. Imagine looking at a horizon that stretches across Pangaea's deserts. You'd see vast red landscapes baked under a hot sun, interrupted by rivers that carried life in narrow ribbons across otherwise barren expanses. The air might shimmer with heat. The plants, mostly hardy and drought-tolerant, stood scattered like lonely sentinels. But follow the rivers, and you'd find lush zones where amphibians thrived, where small reptiles darted in and out, and where the ancestors of the great dinosaurs were only just beginning to stir. The Earth was wide open. Nature's left vacant by extinction, and evolution moved in to fill them. Of course, talking about the Mesozoic as one thing is a bit misleading. It lasted an almost incomprehensible span of time, from about 252 million years ago to 66 million 3 years ago. That's nearly 186 million years of change, of continents shifting, climates transforming, and species rising and falling. To put it in perspective, the entire span of recorded human history is only a few thousand years. Our species has been around for maybe 300,000 years. The Mesozoic was hundreds of millions, a timescale so long that entire mountain ranges could form and erode away within it. To walk through this age is not to stand in one place, but to ride through waves of change. Still, when most people hear Mesozoic, they think dinosaurs, and with good reason. This was their stage. But focusing only on them risks missing the true scale of what Earth was like. Because the Mesozoic was not just the age of dinosaurs, but also the age of new oceans, of continental drift reshaping everything, of evolutionary experiments in the skies and seas, of climates that swayed between greenhouse heat and cooler stretches, of plants, quietly, reinventing the landscape long before mammalian forests like our own ever took root. Try to imagine what the sky looked like. Today, we're used to birds wheeling above us, but back then, the first birds were only just appearing, their feathers more primitive, their flight a bit more clumsy. The rulers of the skies for most of that time were pterosaurs, with wings stretched to a cross, elongated fingers, some as small as sparrows, others as large as small airplanes. They would have circled over coastlines, diving for fish, or scavenging along beaches, their shadows stretching across dunes. Now picture the oceans. You'd see waters alive with reptiles that had abandoned land altogether. Sleek ichthyosaurs, with bodies shaped like dolphins, surged after shoes of fish, while long-necked plesiosaurs moved like living myths, their heads darting from the waves. In the later stretches, great mosasaurs dominated. Massive lizards adapted to marine life, with jaws that could swallow prey whole. The seas themselves were different, too. Coral reefs were built not just by corals, but by strange sponges and by valves. Shells unlike any you've ever seen lay scattered along the shores, and ammonites, spiral-shelled relatives of squid, floated by the millions. On land, the forests were dense with conifers, cycads, ginkgos. Imagine trees rising like pillars, their crowns spreading broad and dark. The ground littered with strange ferns and horsetails taller than you. This was a green world, spucha, scapobat, but not the familiar flowering forests, you know. Flowers hadn't yet taken hold until late in the era, so the landscapes lacked the colors and scents that now seem so natural to us. Instead, they were dominated by greens, browns, grays, and the occasional cones and seeds of gymnosperms. And into this world came the dinosaurs. At first, they were small, almost inconspicuous, competing with other reptiles for survival. But slowly, they began to spread, adapting into new forms. Some walked on 2 legs, some on 4, some mixed the two. Over time, they grew into giants like sauropods, stretching longer than buses, weighing more than any land animal before or since. Alongside them came predators, from small, agile hunters to apex giants like Allosaurus, and later the mighty Tyrannosaurus. But the Mesozoic wasn't just a tale of giants, it was also a time of subtlety, of the first mammals creeping through undergrowth, of insects adapting to new plants, of ecosystems weaving themselves into complexity. Every shift in climate or geography reshaped the balance. As continents broke apart from Pangaea into smaller landmasses, isolation created diversity. The dinosaurs of one region evolved differently from those of another. Life was spreading, branching, filling the earth in ways that still echo today. Even in quiet corners, the Mesozoic left its marks. Rivers carried sediments that hardened into rocks, where we now find fossils. Volcanoes left layers of ash that mark turning points. Every layer of stone from that time is a page of a story we're only now learning to read. When paleontologists brush dirt from a fossil bone, they're holding not just a piece of ancient life, but a fragment of the world itself, one that tells us how Earth looked, smelled, and sounded in that distant age. So, here we are, standing at the edge of this enormous stretch of history, ready to wander through it slowly. The Earth of the Mesozoic was not a single place, but a whole theater of change, an age where life experimented wildly, and the planet itself reshaped the rules. From deserts to swamps, from mountain ranges to shallow seas, from the first fragile steps of dinosaurs to the booming thunder of their dominance, it was a world both alien and familiar, strange yet foundational to everything that came after. And as we drift deeper into it, we'll follow those stories, piece by piece. The rise of the dinosaurs, the sway of forests, the restless oceans, the skies filled with wings, the climate shifts, the slow bloom of flowers, the final catastrophe that ended it all. 'Cause to ask what Earth was like during the Mesozoic is not to get one simple picture, it's to open a long, winding journey, one that spans almost 200 million years of Earth's imagination. When people picture the age of dinosaurs, the mind usually jumps to the giants. Towering sauropods, casting shadows across entire valleys, armored beasts clanking through forests, predators with jaws large enough to snap bone in an instant. But the truth is, for much of their time on Earth, dinosaurs weren't solitary rulers striding across empty landscapes. They were surrounded by neighbors of every imaginable shape and size, living in ecosystems as bustling and complicated as any modern rainforest or savanna. To understand what Earth was like then, you have to look not just at the famous animals, but at the whole stage they shared. Imagine standing in a valley during the Jurassic, the air heavy with the scent of resin from conifers, and the musty dampness of ferns underfoot. To your left, a herd of sauropods moves slowly, their necks swaying high above the canopy as they strip branches bare. But closer to the ground, smaller creatures scurry between tree trunks. Some are tiny mammals, no bigger than mice, darting through the leaf litter at night, their sharp noses sniffing for insects. Others are early lizards, hugging the warmth of rocks, watching wearily for anything that might swoop or pounce. The dinosaurs were there, of course, but they were only one part of a constant negotiation of survival. On the open plains, herds of plant-eating dinosaurs gathered together, much like wildebeest do today. Their footsteps shook the earth, leaving tracks that would fossilize into the stone we now study. But they didn't have the landscape to themselves. Crocodile-like reptiles lurked in rivers and lakes, waiting for the moment a thirsty animal leaned too far toward the water. Flying above, pterosaurs rode thermals, their keen eyes scanning for fish, carrying, or perhaps the chance to pluck up something small and unlucky. And in the soil beneath it all, insects crawled, tunneling and feeding, recycling plant matter, helping the cycle of life continue in ways that rarely get noticed, but matter all the same. The Mesozoic wasn't a tidy story of one group of creatures rising while all others faded into the background. It was a crowded stage, and for a long time, dinosaurs weren't even the obvious stars. In the early Triassic, after the devastation of the Great Extinction, other reptile groups were far more dominant. The ancestors of crocodiles, called pseudowuians, flourished in many forms. Some of them looked like armored tanks, while others ran quickly on two legs, filling niches that dinosaurs wouldn't claim until much later. There were also strange archosaurs with beaked faces, armored backs, and adaptations that seem almost experimental in hindsight, as if evolution was testing designs in a workshop full of prototypes. It's important to picture that early world as uncertain. The Earth was recovering, ecosystems rebuilding themselves. Dinosaurs were small, light-boned, relatively unimpressive compared to the bulkier reptiles of the time. They stayed in the background, surviving quietly, until a shift in climate and environment tipped the balance in their favor. Even then, they never lived alone. Crocodile relatives continued alongside them. Amphibians held on in wet places. Mammals skirred in the dark and in the seas just beyond shorelines. The ichthyosaurs and plesiosaurs reigned without challenge. One of the things that makes this era so fascinating is how interconnected everything was. When we talk about dinosaurs, it's tempting to treat them as isolated wonders, towering curiosities we admire in museums. But in their time, they were simply part of the food web. The The giants that browsed on conifers opened space in forest for sunlight to reach the ground, letting ferns and smaller plants thrive. Predators that hunted those giants left carcasses behind, which scavengers picked clean. Insects carried pollen, spreading the first hints of flowering plants as the Cretaceous unfolded. Every movement had ripples. The neighbors of the dinosaurs weren't just incidental, they were vital in shaping the environment that made dinosaurs so successful. Picture a late Cretaceous wetland. Herds of hadrosaurs gather along the water's edge, their duck-billed faces dipping to graze on plants. Their calls echo across the swamp, low and resonant communication between parents and offspring, warnings of predators, or perhaps simply social chatter. But between their legs, mammals are busy. Some are burrowers popping in and out of tunnels, others climb through low shrubs, their small hands grasping stems as they seek seeds or insects. Crocodiles slide quietly into the water, eyes just breaking the surface. And above it all, pterosaurs with wingspans longer than a car patrol the skies. This is no lonely kingdom, it's a crowded, layered world where everything has a place. Even the plants themselves played the role of neighbors. Early in the Mesozoic, the landscapes were dominated by gymnosperms, plants like cycads, conifers, and ginkgos. These trees and shrubs gave structure to the forests, but they didn't offer the same kinds of resources we associate with modern ecosystems. There were no flowers for bees to gather from, no fruits dangling to tempt mammals or birds. Yet, life found its way. Insects adapted to gymnosperms, reptiles grazed cycads, and dinosaurs browsed high branches that no other creature could reach. When flowering plants finally appeared in the Cretaceous, the entire rhythm of life changed. Flowers attracted pollinators, seeds became food for new species, and the variety of neighbors multiplied almost overnight in evolutionary terms. When you think about it, this web of neighbors is what makes the Mesozoic so much like the modern Earth. It's easy to imagine a dinosaur stomping through an empty forest, but that was never the case. Just as today, no animal exists in a vacuum, every creature is surrounded by others, sharing space, competing for food, shaping and reshaping their environments. Dinosaurs had neighbors at every turn, some allies, some threats, all part of the same unfolding story. The seas during this time remind us of that balance too. While land was the stage for dinosaurs, the oceans were a completely separate arena. Marine reptiles dominated here, their sleek bodies cutting through waves. Ammonites with their beautiful spiral shells floated by the millions prey for larger hunters. Fish schools darted in dense clouds, while sea urchins and crustaceans scuttled across the time. Seafloor, it was a world as diverse and noisy as any coral reef today, and though dinosaurs never set foot in it, their world was tied to it. Ocean currents influenced climate. Coastal changes created new habitats, and the rising and falling seas shaped where land animals could live. Even insects deserve their place in this picture. They were some of the most constant companions of dinosaurs, buzzing through the air, burrowing in the soil, feeding on plants, and occasionally on each other. Dragonflies the size of hawks no longer soared as they had in earlier ages, but beetles, flies, and early relatives of butterflies flourished. They were pollinators, decomposers, and sometimes pests, always there, always shaping the way life worked. Dinosaurs lived in a world where the hum of insects was as steady as the sound of the wind. And then there were the mammals, too often dismissed as tiny, unimpressive creatures waiting quietly for the dinosaurs to vanish. They were in fact lively, adaptive neighbors. They experimented with climbing, burrowing, gliding. They developed sharper senses for the night, thriving in the hours when the great reptiles slept. Some hunted insects, others ate plants. Still others may have been opportunistic omnivores. Their size kept them out of the spotlight, but their resilience meant that when the Mesozoic finally closed with catastrophe, they were ready to step forward. Standing back and looking at the whole scene, it becomes clear that the age of dinosaurs was less about one group ruling alone and more about an entire Earth busy with life. Each creature was tied to others. Each environment was filled with layers of relationships. The dinosaurs may be the ones we notice most now, but their neighbors tell us just as much about what kind of world the Mesozoic really was. It was a world of sharing, of competing, of adapting side by side. And the longer you linger in that image, the more you realize that it isn't so different from the present. We too share our world with countless neighbors, most of them unnoticed. From insects recycling the soil beneath us, to birds filling the skies above, the dinosaurs lived in a world woven from countless threads, and in many ways, so do we. If you were to lay out the timeline of Earth's history on a single ribbon, the Mesozoic would stretch across it like an endless middle passage, long enough that entire civilizations could rise and fall 1,000 times within it, and still not make a dent in its duration. When people call it the Age of Reptiles, they're not exaggerating, though it was far more than dinosaurs alone. Reptiles in every imaginable form dominated land, sea, and sky, adapting to roles that would last for millions upon millions of years. To understand why it earned that name, you have to sit with just how long it lasted and how much change could take place within a span so vast. The story begins after the Earth had staggered through its greatest dying. The Empyrean extinction had swept the board clean, and from those empty spaces came opportunity. In the early Triassic, reptiles of many kinds began to fan out into the open niches. Some stayed small, hugging the ground. Others grew into bulky armored forms, and some began experimenting with bipedal strides that would set the stage for dinosaurs. But in those first tens of millions of years, no single group truly dominated. It was a period of reshuffling, ecosystems reforming themselves from the ruins, and every new form seemed to test the possibilities of survival. As the Triassic wore on, certain lineages began to emerge as clear successes. Among them were the ancestors of crocodiles, robust and diverse, many walking upright on long legs, filling roles from fast predators to heavily armored plant-eaters. Alongside them, early dinosaurs were small, quick, and hardly the ruling giants they would later become. In fact, if you stood on the bank of a Triassic river and looked out, you might have been more impressed by the crocodile cousins and the odd armored reptiles than by the scurrying, two-legged creatures we now revere. But the world doesn't stay still. Shifts in climate, geography, and mass extinctions tilted the balance again and again. At the end of the Triassic, another wave of extinction cleared the stage of many dominant reptiles, including a great number of those crocodile relatives, leaving room for dinosaurs to step forward. And step forward they did, expanding in size, shape, and ecological role until they became the towering, thundering figures that define the Mesozoic in our imagination. From that point onward, reptiles of all stripes held sway across the globe. The land belonged largely to dinosaurs, their diversity staggering when you consider the full span of their reign. On one continent, long-necked sauropods stretched toward the highest branches. On another, horned and frilled creatures grazed across plains. Swift raptors dashed through forests, while enormous predators waited patiently in the shadows. But they were not alone. In the seas, marine reptiles grew sleek and powerful, replacing fish and sharks at the top of the food chain. And above, pterosaurs spread their membranous wings, claiming the skies long before birds had truly found their stride. It's almost dizzying to consider how long these patterns lasted. If you think about the time since humans first began building cities, you're talking about maybe 10,000 years. If you stretch back to the earliest Homo sapiens, 300,000 years, the Mesozoic spanned nearly 200 million years. Within that time, entire groups of dinosaurs appeared, thrived, and disappeared without ever brushing against the edge of human history. The reign of sauropods alone lasted tens of millions of years, longer than mammals, as a group have yet been dominant. To the Earth, dinosaurs weren't a fleeting experiment. They were the long-term residents, the standard by which entire ecosystems were measured. And yet, Calling it the Age of Reptiles is not to forget the quieter neighbors who never left the stage. Mammals were there, small and persistent, their story running parallel to the giants. Amphibians held on in wetlands, adapting to shrinking roles, but never quite vanishing. Insects buzzed endlessly, evolving new shapes to match the plants that were beginning to diversify. Still, it was reptiles in all their forms that set the tone. Their bodies became the architecture of ecosystems, shaping forests, plains, rivers, and coastlines through sheer presence. Think about the seas for a moment. For most of the Mesozoic, reptiles ruled them in ways fish never had. Ichthyosaurs darted like living torpedoes, some species reaching the size of buses. Plesiosaurs with necks like serpents weaved through shoes of fish, their bodies propelled by flippers that looked almost too awkward to be effective, but carried them swiftly nonetheless. Later, mosasaurs, immense marine lizards, surged into dominance, snapping through schools of prey with jaws lined with teeth that curved backward to prevent escape. These were not side stories. For millions upon millions of years, if you wanted to picture the ocean's apex hunters, you wouldn't think of sharks or orcas. You'd think of reptiles. And in the skies, pterosaurs rose to prominence, with a grace that is easy to underestimate when you look at their fossils. With wingspans that eventually stretched over 10 meters, they were some of the largest flying animals ever to exist. Some soared like modern seabirds, gliding vast distances over coastlines. Others flitted about like bats hunting insects. They occupied niches from the tiniest aerial hunters to the grandest skylords, and they did so for over 150 million years. Birds may have taken over eventually, but pterosaurs held the skies for far longer than birds have yet managed. On land, the sheer variety of dinosaur forms is what makes the Age of Reptiles such an accurate label. From armored stegosaurs with their plates and spikes, to duck-billed hydrosaurs with elaborate crests, to predatory giants like Spinosaurus that may have stalked both water and land, the creativity of evolution during this time feels almost endless. They weren't just big lizards stomping through forests. They were specialists adapted to climates ranging from arid deserts to damp swamps, thriving on continents that were splitting and drifting apart, creating new opportunities for isolation and diversification. One way to appreciate the length of this age is to remember that the world itself transformed around them. At the start of the Mesozoic, all the continents were fused together in Pangaea. By the end, they had begun to resemble the arrangement we recognize today. Dinosaurs didn't simply live through this change. They adapted to it. As land masses split apart, populations became isolated, evolving into distinct species. That's why we see such different lineages in South America compared to Asia or North America compared to Africa. The breaking of the supercontinent gave rise to new environments, and reptiles of every form responded in kind. Climate, too, shifted dramatically. In the early Triassic, the world was hot and dry, deserts sprawling across vast interiors. Later, during the Jurassic, climates grew more humid, forests spreading across much of the globe. By the Cretaceous, greenhouse conditions prevailed, sea levels high, shallow seas flooding continents and creating warm, lush environments. Through all of this, reptiles adjusted, expanded, and thrived. It's hard to think of another group of animals so flexible, so capable of molding themselves to every change the planet threw at them. It might be tempting to ask why reptiles, in particular, came to dominate in this way. The answer isn't simple. Part of it has to do with timing. They happened to survive the great extinctions when others did not. Part of it lies in their physiology, their ability to adapt to different climates, to lay eggs on land, to grow into a staggering range of sizes and forms. And part of it is simply the way evolution works, with small advantages compounding over long stretches until they reshape the entire structure of life. Once reptiles gained a foothold, their momentum carried them through epoch after epoch. But perhaps the most striking thing is that for all their dominance, they were never static. The Mesozoic wasn't a single frozen moment, where reptiles ruled unchallenged. It was a constant dance of rise and fall, of new groups emerging and old ones fading. The armored stegosaurs of the Jurassic gave way to the horned ceratopsians of the Cretaceous. Small, agile predators in one age were replaced by towering tyrannosaurs in another. Each wave left fossils behind, like bookmarks in the stone. Remind us that even in an age of apparent stability, change was always underway. When paleontologists talk about this being the age of reptiles, they're summarizing almost 200 million years of dominance of creatures that filled nearly every ecological role the ptarmidans had to offer. It's a reminder of how long the Earth has been reshaped by forces and lives we can barely comprehend on human scales. And it sets the stage for everything that followed. Because without that immense span, without the reptiles that wove themselves into every corner of land, sea, and sky, the world we live in now would not exist. If the land during the Mesozoic was busy with the sound of footsteps, calls, and rustling plants, the seas were no less alive, only their voices carried differently. Beneath the waves, life continued its experiments, shaping forms that would seem fantastic to our eyes, but were simply the norm in their own time. To imagine these oceans is to imagine a world both alien and strangely familiar, full of predators and prey, of migrations and cycles, of the ceaseless push and pull that defines every marine ecosystem. The phrase ancient seas might suggest quiet waters, but the truth is, they were anything but quiet. They were in motion, endlessly dynamic, with creatures that claimed their own kind of dominance long before mammals ever considered the shoreline. At the very beginning of the Mesozoic, after the devastation of the Pangaea extinction, the oceans were nearly empty. Coral reefs had collapsed. Many shellfish and fish species had been wiped away, and the water itself had been left chemically unstable for long stretches. But as the Triassic dawned, the seas slowly rebuilt themselves. New kinds of corals returned, sponges took hold, and mollusks diversified again. Shoals of fish began to recover, darting in patterns that would soon attract larger hunters. In this fresh slate of opportunity, reptiles ventured in, testing the waters, not as visitors, but as residents. Among the first of these marine reptiles were the ichthyosaurs. Their ancestors likely began as land-dwelling reptiles that slowly adapted to coastal life, hunting in shallows before diving deeper and deeper until they were fully aquatic. Within a few million years, they had streamlined bodies shaped so much like dolphins that if you saw one at a distance, you might mistake it for a modern mammal. Long snouts, lined with sharp teeth, enormous eyes adapted for dim underwater light, and tails that moved them forward with startling speed made them some of the most efficient predators of start. Their age. They thrived through the Triassic and into the Jurassic, and some species grew to the size of buses, true giants of the seas. But iosaurs weren't alone. Around the same time, another group of reptiles began to adapt to aquatic life, eventually giving rise to the plesiosaurs. Unlike the sleek ichthyosaurs, plesiosaurs came in different body plans. Some had long, snake-like necks and small heads, ideal for darting after fish or squid with quick snaps. Others had shorter necks and larger heads with powerful jaws, better suited for taking down larger prey. All of them used their limbs, transformed into flippers, to propel themselves through the water, in a motion almost like the underwater flight of sea turtles. They became some of the most iconic marine reptiles, their silhouettes instantly recognizable in fossils and reconstructions. The seas were not limited to reptiles alone. Ammonites, distant relatives of squid and octopuses, floated in vast numbers. Their coiled shells varied in size, from small spirals that could fit in your palm, to massive ones nearly a meter across. They were prey for larger hunters, but also hunters themselves, using tentacles to grab smaller creatures. Their shells have become some of the most common fossils from the Mesozoic, recording not just their presence, but also the rise and fall of entire ecosystems. Their cousins, the belemnites, resembled squid more closely. streamlined for chasing through open water. Together, ammonites and bellites filled the seas, their populations waxing and waning with the fortunes of the reptiles and fish around them. Reef ecosystems slowly re-established themselves too. Instead of the coral reefs we know today, Mesozoic reefs were often built by rudest clams, strange bivalves that grew into pillars and towers, creating entire underwater landscapes. These reefs supported countless fish, crustaceans, and invertebrates, just as modern reefs do, forming hubs of biodiversity that attracted predators from far and wide. Imagine swimming through one of these reefs. The shapes would be odd, unfamiliar, but the effect the same. Walls and crevices teeming with life, schools of fish darting in and out, predators circling the edges, waiting for an unwary meal to stray too far. As the Jurassic gave way to the Cretaceous, the seas became even more restless. Global temperatures were warm, sea levels high, and shallow inland seas flooded across vast portions of the continents. North America, for example, was split in two by the Western Interior Seaway, a broad, shallow ocean stretching from the Arctic all the way to the Gulf of Mexico. These inland seas became highways for marine reptiles, rich hunting grounds for fish and ammonites, and safe nesting areas for seabirds that were beginning to appear. They connected ecosystems across continents, creating opportunities for species to spread and diversify. In these waters, a new kind of reptile surged to dominance, the mosasaurs. Descended from land-dwelling lizards, mosasaurs adapted astonishingly quickly to life in the sea. They grew massive, some exceeding 15 meters in length, with jaws that could open wide enough to swallow large prey whole. Their bodies were muscular, their tails long and powerful, making them some of the fastest hunters in marine history. In some ways, they filled the role that orcas and great white sharks hold today. Apex predators with few rivals. Fossils even show the remains of other mosasaurs inside their stomachs, evidence that they preyed on each other as much as on fish and ammonites. The oceans of the Mesozoic were also stages for countless fish lineages that still shape the seas today. Early tyosts, the ancestors of most modern fish, began to diversify in the Jurassic, and especially in the Cretaceous. Their adaptability gave them an edge, allowing them to explore different feeding strategies and habitats. Sharks too persisted, though they were often overshadowed by the reptilian giants. They hunted, scavenged, and waited in the shadows. Their cartilaginous skeletons rarely fossilized, but their teeth leaving a record in the rocks. Even the smallest organisms played their part. Plankton, microscopic plants and animals floating in the sunlit layers of the sea, formed the foundation of marine food webs, as they do now. Their populations influenced the abundance of fish, which in turn shaped the success of the reptiles that hunted them. Tiny shells of plankton settle to the seafloor, accumulating over millions of years into chalk, deposits so vast that entire regions of Europe are built from them. The white cliffs of Doha, a lasting monument to the life of Cretaceous seas. What stands out when you try to picture all this is the sheer energy of those oceans. They were not empty backgrounds to the drama on land, but equal stages of their own, with rivalries, strategies, and balances that lasted longer than any human empire ever could. A school of fish might flash silver under the surface, only to be scattered by the strike of an ichthyosaur. A plesiosaur might raise its head above the waves, eyes scanning for danger. A mosasaur might burst upward, jaws snapping around prey, before vanishing again into the depths. Every day, every tide, every migration was part of a rhythm that defined life during the Mesozoic just as much as dinosaurs did. And those oceans, always shifting, influenced the land too. The rise and fall of sea-level-shaped coastlines altered climates, and created or destroyed habitats. Shallow seas warmed the air above them, making nearby continents lush and humid. When they receded, climates grew harsher, deserts expanded, and ecosystems had to adapt. The motion of the oceans was not just within the waves, but across the entire planet. A reminder that water and land are never fully separate. The creatures of those seas left behind more than fossils. They left echoes of themselves in the animals we see today. Modern whales, with their streamlined shapes and hunting strategies, recall the ichthyosaurs, sea turtles flapping steadily through open water mirror plesiosaurs in motion. Monitor lizards with their muscular builds and powerful jaws are close cousins of mosasaurs. Even the fish and sharks of our time are descendants of those that swam beneath reptilian shadows. To study the ancient seas is to see the roots of the oceans we know now, shaped across millions of years of reptilian rule. And when you think of the Earth as a whole during this age, the seas remind you that it was never just about dinosaurs, never just about the creatures on land. The oceans were equal partners in the story, in constant motion, hosting their own empires that rose and fell with the tides. They may have been hidden from the eyes of the land dwellers, but they were no less important, no less vibrant, no less full of the relentless drive of life. When people think of the Mesozoic, they often picture the dinosaurs as if they moved across empty plains, their bodies towering in isolation against a bare landscape. But the truth is, they lived within forests and swamps, and open spaces filled with plants that built the structure of their world. These plants were not the same ones you would recognize today. The flowers, fruits, and grasses that feel so ordinary to us were either absent or only beginning to appear. Instead, the earth was green in an entirely different way, with forests dominated by conifers, cycad, ginkgos, and ferns, a vegetation that gave the planet its character for nearly 200 million years. To imagine dinosaurs is to imagine them not just as animals, but as part of these forests of giants. If you walked into a forest in the Triassic, the first thing you might notice is how different the air felt. Oxygen levels fluctuated across the Mesozoic, sometimes higher than today, sometimes lower, and the mix of volcanic activity and plant growth kept the chemistry of the atmosphere in constant flux. The scent would not be one of flowers, because flowers were not yet part of the scenery. Instead, the air would be thick with the rainous smell of conifers and the earthy dampness of ferns. The ground beneath your feet would be littered with cones and needles rather than petals. It was a world of greens and browns, with occasional splashes of color from seeds or cones, but not the riot of blossoms we take for granted in modern ecosystems. Conifers were among the dominant trees of the age, relatives of pines, firs, and redwoods. They grew tall and straight, forming the backbone of many forests. Some species reached enormous sizes, their trunks as wide as small houses, their crowns forming canopies that shaded entire ecosystems beneath them. These trees offered shelter to countless creatures, from insects burrowing in bark to reptiles climbing in branches, and they fed the giants too. Sauropods, with their necks stretching upward, browsed among these trees, stripping needles and branches with every movement. The relationship between the towering plants and the towering animals was as close as any ecological connection can be, one shaping the other through countless generations. Cycads were another signature of the landscape. These plants look something like palms, but were unrelated, with thick trunks topped by spirals of stiff leathery leaves. They were ancient, tracing their lineage back long before the Mesozoic. But during this era, they flourished. In some regions, entire groves of cycads covered the land, their crowns catching the sunlight, and their seeds offering food to animals that could crack them open. Imagine a plain scattered with cycad, like a green fountain frozen in place. And across that plain, herds of dinosaurs moving slowly as they grazed. Then there were the ginkgos. Today, only a single species survives, planted in cities and gardens as a living relic. But in the Mesozoic, they were far more diverse. Their fan-shaped leaves spread out in forests across the northern hemisphere, their branches filling the air with shapes that are instantly recognizable even now. The seeds they produced were large and nutritious, likely eaten by reptiles and early mammals alike. Their resilience is part of why one still remains today. unchanged in form, for over 200 million years, a witness that connects our world to theirs. Ferns, horsetails, and seed ferns filled the undergrowth. Ferns in particular thrived in moist places, carpeting the forest floor, climbing the sides of larger trees, and offering shelter to countless smaller animals. Horsetails grew in dense stands, some taller than a person, their segmented stems forming thicket along rivers and swamps. These plants had already been on Earth for ages before the Mesozoic began, but they adapted to the new world, continuing to provide the green fabric that supported herbivores at every scale. For most of the Mesozoic, these were the plants that defined life. They offered food, shade, shelter, and oxygen. They were the scaffolding of ecosystems. Without them, the dinosaurs we know so well would never have reached their sizes. A sauropod could grow enormous because there was enough plant matter to support its bulk. Hadrosaurs could graze in herds because cycads and conifers offered them constant supplies of foliage. Even predators depended on these forests indirectly because their prey drew strength from the plants that grew across continents. And then, late in the story, something entirely new appeared. Flowering plants or angiosperms entered the scene in the Cretaceous. At first they were small, not much competition for the great forests of conifers and cycads, but their advantages soon changed everything. Flowers offered a new strategy for reproduction, attracting insects and later birds to carry pollen, making them more efficient than wind-pollinated gymnosperms. Fruits developed as another strategy, enticing animals to eat them and spread their seeds. Within tens of millions of years, flowering plants spread across the world, reshaping ecosystems in ways that are still with us today. The arrival of flowers also shifted the insect world. Bees had not yet evolved, but other pollinators began to adapt to the opportunities flowers presented. New relationships formed, new food webs spread outward, and suddenly the landscapes gained colors that had never been seen before. What had been a world of green and brown slowly transformed into one with bursts of yellows, reds, and purples. Dinosaurs themselves may have noticed, feeding on early fruits or seeds, carrying pollen on their skin without even realizing it. The forests of the late Cretaceous were no longer the same as those of the Triassic. They were busier, brighter, and more interconnected. One of the most striking things about these forests is how they reveal the continuity of life. Many of the plants that dominated and still exist in some form now, conifers remain in our pine forests. Cycads survive in tropical regions, often as rare species, clinging to survival. Ginkgos still grow in parks and gardens, living fossils that remind us of their ancient heyday. Even ferns and horsetails persist, their forms barely changed from the days when dinosaurs walked among them. To look at these plants today is to glimpse directly into the Mesozoic, to see something that has endured for over 200 million years. And when you try to picture dinosaurs in their habitats, it's these forests of giants that give them context. A sauropod without a tree to reach for is only half a picture. A hadrosaur without cycads to graze seems incomplete. Even the predators make more sense when you imagine them stalking through ferns, waiting in the shadows beneath conifers, or chasing prey across open groves of ginkgos. The plants were not just background scenery. They were the stage itself, shaping every movement of the play. The climate of the Mesozoic gave these plants the conditions they needed. For much of the era, greenhouse conditions prevailed. Temperatures were warm, polar regions lacked permanent ice, and forests reached nearly to the poles. Fossilized wood and leaves have been found in what are now Arctic and Antarctic regions, showing that even there, lush vegetation grew in conditions we would not associate with icy wastes. Dinosaurs lived in those forests too, adapted to long seasonal darkness, but never to frozen tundras. The plants tell us this clearly, their fossils marking the boundaries of climates that were far warmer than ours today. And yet, the forests were not uniform. In dry interiors, hardy conifers dominated. In wetter lands, ferns and horsetails spread along coasts and riverbanks. Cycads grew in dense stands. Each region had its own pattern of vegetation, and each pattern supported its own mix of animals. Just as today, the diversity of plants created the diversity of animals. Where plants spread wide, herbivores thrived, and where herbivores thrived, predators followed. The forests were the foundation, and everything else was built on them. Thinking about these forests also changes how we imagine time itself. Plants grow slowly, their trunks thickening year by year, their rings recording changes in climate. Some conifers in the Mesozoic may have lived for centuries, standing in the same place as generations of dinosaurs passed beneath them. Imagine a tree that sprouted when one group of dinosaurs ruled, still alive when another group had taken their place, still standing when an entire lineage had gone extinct. These trees were witnesses to spans of time that dwarf our own lifetimes, steady presences in a world of constant motion. Even their fossils remind us of this patience. Petrified forests, where minerals replaced wood cell by cell, capture the shape of trunks that once stood tall. Leaf impressions pressed into stone show the delicate shapes of ginkgo fans or cycicad. Fronds, cones fossilized in fine detail, tell us exactly what these plants looked like, as if time itself had paused for a moment to preserve them. Through these traces, we can reconstruct the forest of giants, not as vague scenery, but as living ecosystems. The plants of the Mesozoic were giants, not just in size, but in significance. They structured the world, provided the resources, and set the stage for everything else. Without them, the dinosaurs would have had no food, no habitats, no opportunities to grow into the shapes we marvel at today. The forests carried the age as much as the animals did. Their roots sunk deep in the soil, their crowns spread across the skies, their lives intertwined with every creature that walked, flew, or swam nearby. And so when we think of the Mesozoic, we must picture not just the animals, but the greenery that surrounded them, because to see the forests is to see the age more clearly, to understand the world as it truly was, alive with giants of wood and leaf, as much as with giants of bone and muscle. When you think of the Mesozoic, the images that come most easily are usually of creatures moving through forests or across plains. But just as important as the ground beneath their feet was the air they breathed. The chemistry of the atmosphere, the levels of oxygen and carbon dioxide, the temperature of the planet, the storms, the rainfall, the droughts, all of it shaped the possibilities of life. The plants that grew, the animals that thrived, the way ecosystems formed and broke down were guided by the atmosphere above them. To understand what Earth was like during those long millions of years, you have to imagine not only the sights, but also the invisible conditions that made them possible. At the dawn of the Mesozoic, the Earth was still recovering from devastation. The Great Extinction at the end of the Permian had disrupted every part of the biosphere, and the atmosphere was no exception. Volcanic eruptions on massive scales had poured gases into the air. Carbon dioxide levels were high, and global temperatures soared. The early Triassic was a hot, arid time, with many regions reduced to deserts. Rain was scarce, and much of the supercontinent of Pangaea baked beneath the sun. If you had been there, you would have felt heat radiating from the ground, seen skies often hazy with volcanic dust, and breathed an atmosphere thick with carbon dioxide. As the Triassic moved on, things began to stabilize. Oxygen levels, which had dropped dangerously low after the Permian extinction, slowly began to rise again. Plants spread across the land, drawing carbon dioxide out of the air and giving oxygen back in return. Still, the balance was not the same as today. Oxygen was often lower and carbon dioxide higher, a mix that made the climate warmer overall. The interiors of continents stayed dry, while coastal regions and river valleys grew greener. This unevenness shaped the kinds of animals that could survive. Reptiles with efficient lungs and bodies adapted to heat had the advantage. Mammals, still small and mostly nocturnal, found safety in the cooler hours of night. By the Jurassic, the atmosphere had shifted again. Oxygen levels rose, in some estimates, even higher than modern levels, while carbon dioxide remained elevated enough to keep the world warm. These conditions encouraged the spread of lush forests and allowed animals to grow larger. When you look at the massive sauropods of the Jurassic, you're seeing not just an evolutionary experiment, but also the result of a supportive atmosphere. Higher oxygen made it easier for large animals to fuel their enormous bodies. Elevated carbon dioxide coupled with warm climates allowed plants to grow rapidly, producing the vast quantities of food needed to support herds of giants. The very air itself was part of the reason dinosaurs could reach sizes beyond anything seen, before or since on land. The climate of the Jurassic was different across regions, but generally wetter than the early Triassic. Monsoons swept across the interiors of continents, bringing seasonal rains. Forests spread more widely, ferns and conifers filling lands, sinked plains. The humidity supported amphibians, still clinging to the edges of ecosystems, and the warmth meant reptiles thrived nearly everywhere. Even the polar regions, though experiencing long stretches of darkness in winter, were mild enough to host forests. Fossilized wood found near the poles shows that ginkgos and conifers grew there, creating seasonal forests where dinosaurs adapted to months without sunlight, but not to cold. The Earth was warmer than today from equator to pole. The greenhouse effect, strong and steady. The Cretaceous, the final stretch of the Mesozoic, brought yet another atmospheric shift. Carbon dioxide levels climbed even higher, in some estimates reaching 4 to 6 times modern levels. The greenhouse climate intensified, sea levels rose, and shallow seas spread across continents. Warm, humid conditions reached into regions that are dry today. North America, split by the western interior seaway, became a patchwork of coastlines, river deltas, and wetlands. Europe was a chain of islands. Forests flourished in these conditions, and flowering plants having emerged in the early Cretaceous spread rapidly. The air would have carried new scents, the sweetness of flowers mixing with the resin of conifers, a change in the atmosphere, not just in chemistry, but in experience. Oxygen levels in the Cretaceous fluctuated, but in general, they remained higher than in the Triassic. This balance of abundant oxygen and high carbon dioxide created unique conditions for life. Large animals continued to thrive, and ecosystems supported enormous biodiversity. The warm, stable climate reduced the likelihood of ice at the poles, and indeed, no evidence suggests permanent ice sheets existed during the Mesozoic. Instead, the world was largely ice-free, with tropical and subtropical climates stretching far toward the poles. Storms in this greenhouse world could be intense. With higher global temperatures came stronger evaporation, more moisture in the air, and greater rainfall in many regions. Monsoon systems may have been more powerful, sweeping across inland seas and flooding low-lying areas. Yet at the same time, some regions remained arid, deserts stretching across continental interiors where rain rarely reached. The climate of the Mesozoic was not uniform, but varied with wet and dry zones, lush coasts, and barren interiors, all shaped by the chemistry of the atmosphere above. The air itself may have felt different to breathe. With higher carbon dioxide, plants grew rapidly, but also exhaled more chemical compounds. Some of these may have filled the air with stronger scents of resin, sap, or even bitterness from defensive chemicals. The smell of a Mesozoic forest was not the floral fragrance we know today, but something more pungent, more earthy, a mix of conifer resin, fern spores, and the must of damp soil. Breathing in that world would have been to taste the raw chemistry of a different balance of gases. Volcanoes played a constant role in shaping this balance. Throughout the Mesozoic, eruptions poured gases into the air, both sustaining high carbon dioxide levels and triggering periodic disruptions. Massive volcanic provinces, such as those that erupted near the end of the Triassic and the end of the Cretaceous, altered the climate dramatically. They could warm the planet by releasing greenhouse gases, but also cool it temporarily by filling the sky with ash and sulfur particles that reflected sunlight. These swings, sudden on geological timescales, stressed ecosystems and sometimes contributed to extinctions. The air was not always steady, but often in flux, a reminder that Earth's climate system is tied directly to the restless geology beneath our feet. Even the winds were different, with continents arranged differently. Ocean currents and atmospheric circulation patterns followed unfamiliar paths. The supercontinent of Pangaea created extreme climates in its interior during the Triassic. But as it broke apart, new coastlines appeared, new currents formed, and climate shifted. Inland seas of the Cretaceous created regional climates far more humid than the same latitudes experienced today. To stand in those times would have been to feel familiar winds in unfamiliar places, monsoons where deserts are now, tropical breezes where temperate forests stand today. The atmosphere also influenced evolution in quieter ways. Insects, for example, grew larger in periods of high oxygen, their bodies able to support greater sizes thanks to more efficient diffusion of oxygen through their tissues. Fossils of dragonflies and other insects from earlier periods show wingspans larger than any seen today, though by the Mesozoic oxygen levels had stabilized enough to limit this gigantism. Still, variations in atmospheric composition subtly shape the possibilities of size, metabolism, and behavior for countless species. Dinosaurs themselves were products of this air. Their lungs, more efficient than those of mammals, allow them to thrive in conditions of lower oxygen that would have challenged us. Their body sizes were sustained by abundant vegetation made possible by high carbon dioxide. Their distribution across the globe was guided by warm climates that extended to the poles. The atmosphere was not just a background, but a partner in their success. By the end of the Cretaceous, the atmosphere was once again in turmoil. Massive volcanic eruptions in what is now India. The Deccan traps poured gases into the sky, warming the planet and altering ecosystems. Then an asteroid impact added to the disruption, throwing dust and vapor high into the air, blocking sunlight and causing global cooling. The air that had sustained the age of reptiles turned against them in those final years, contributing to their extinction. And yet in the long view, the atmosphere of the Mesozoic was remarkably stable compared to some earlier periods. For nearly 200 million years, Earth remained warm, largely ice-free, and rich enough in oxygen to support life on a grand scale. The consistency of those conditions allowed reptiles to dominate, plants to spread, and ecosystems to flourish. The air and climate of the Mesozoic were not just invisible details, but the foundation of the entire age. When we breathe today, we draw in a mixture of gases shaped by billions of years of life and geology. In the Mesozoic, every breath taken by a dinosaur, every breeze that rustled a seaweed grove, every storm that swept across an inland sea was part of a different balance, one that sustained a world both alien and familiar. To imagine that air is to imagine the age more fully, not just as sights and sounds, but as the atmosphere itself, the very breath of the world that carried life forward. The Triassic begins in the shadow of loss. The Earth had just endured the most devastating mass extinction in its entire history. The event at the end of the Paran period that left the planet scarred and emptied. Oceans had been stripped of most of their life. Reefs collapsed, and the land was left barren where once forests and swamps had stretched. Up to 90% of marine species and a huge portion of land animals were gone. For a time, the world must have seemed almost quiet, with ecosystems broken, food webs severed, and the survivors scattered. To imagine the dawn of the Triassic is to picture a planet that was starting over, not from scratch, but from fragments of what had come before. The atmosphere was still reeling. Volcanic eruptions had poured gases into the air, leaving the climate unstable. Carbon dioxide levels were high, oxygen levels low, and global temperatures hot. Much of the supercontinent of Pangaea was dry, its interior a vast expanse of deserts broken only by occasional rivers and lakes. The coasts, where moisture was more reliable, supported pockets of greenery, but much of the land was harsh. Plants were among the first to re-establish themselves, spreading wherever conditions allowed. Ferns often led the way, growing quickly and disturbed ground, followed by hardier conifers and cycads that could withstand drought. Slowly, landscapes that had been stripped bare began to green again. The animals that survived had to adapt to a world with little stability. Amphibians, though diminished, still lived along rivers and lakes, some of them large enough to prey on fish and small reptiles. Early reptiles of many forms filled the gaps left by extinction. Some grew into bulky armored herbivores, their bodies covered in protective plates. Others became quick-footed predators, hunting insects and small vertebrates. The Triassic was full of experiments, lineages, trying new body plans, new diets, new strategies, many of which would vanish without descendants. It was a time of trial and error, with success measured not in dominance, but in persistence. Among the most important survivors were the Pterosaurs, a group of reptiles that included the ancestors of crocodiles, pterosaurs, and dinosaurs. In the early Triassic, they were not yet dominant. Many Pterosaurs were small and inconspicuous, competing with other reptile groups for space, but they carried traits that would eventually give them an edge: efficient lungs, upright postures, and versatile body plans. For tens of millions of years, they existed alongside other reptiles that seemed stronger, larger, or better adapted. Yet, they held on, waiting for their moment. The oceans also rebuilt themselves. Early in the Triassic, they were still harsh places, often warm and oxygen-poor, limiting what could survive. But gradually, new lineages of fish spread, and marine reptiles ventured into the water. Ichthyosaurs began their rise, their bodies still somewhat clumsy compared to the sleek hunters they would become, but already adapting to a fully aquatic life. Nothosaurs, another group of semi-aquatic reptiles, swam through shallow seas, hunting fish with long jaws. Ammonites returned in great numbers, filling the oceans with their coiled shells and tentacled bodies. Piece by piece, marine food webs reassembled. On land, the first large herbivores of the Triassic were not dinosaurs, but other reptiles, including relatives of crocodiles that grew into armored giants. Some walked on 4 sturdy legs, others rose on 2, their bodies covered with protective plates. They grazed on cycads and conifers, spreading across plains and forests. Predators, too, were often crocodile relatives, some of them running on 2 legs, chasing prey with speed and agility. For much of the Triassic, these animals, not dinosaurs, were the rulers of the land. Something too nice, but the Triassic was a long stretch of time, spanning nearly 50 million years, and change was constant. As the period wore on, dinosaurs began to appear. At first, they were small, light, and fast, hardly impressive compared to the massive reptiles around them. They hunted insects, small vertebrates, and perhaps scavenged where they could. Yet, they carried traits that allowed them to expand. Their upright legs let them run efficiently. Their lungs supplied them with oxygen more effectively, and their bones were light but strong. Slowly they spread, at first in the background, then in greater numbers, until by the end of the Triassic, they were poised to take over. The world they lived in was still strange. The supercontinent of Pangaea meant there were no barriers to dispersal. Animals could, in theory, walk from one end of the world to the other, from what is now North America, across Europe, Asia, and down into Africa. This meant ecosystems were more uniform, with similar species spread widely. It also meant that climate extremes were stronger. The interiors of Pangaea were hot and dry, deserts stretching farther than the eye could see, while the coasts were wetter and greener. Life clustered where water was available, leaving vast expanses nearly barren. Volcanic activity was common, and the earth itself seemed restless. Lava flows spread across landscapes, while earthquakes reshaped coastlines. These forces were destructive, but they also created new opportunities. Fresh lava fields were colonized first by ferns, then by hardier plants, starting the cycle of recovery again and again. The Triassic was not a time of stability, but of resilience, where survival meant enduring constant change. Toward the end of the Triassic, another crisis arrived. Around 2011 million years ago, massive volcanic eruptions associated with the breakup of Pangaea poured gases into the atmosphere again. Carbon dioxide spiked, climates shifted abruptly, and ecosystems collapsed. Many of the dominant reptile groups of the Triassic were wiped out, including most of the crocodile relatives that had ruled the land. Dinosaurs, though not yet dominant, survived and suddenly found themselves in a world of open niches. The extinction that closed the Triassic was their opportunity, and in the Jurassic that followed, they began their rise to true dominance. But to stay with the Triassic itself is to remember that it was not a prelude, but a full age in its own right. It was the time when life rebuilt after disaster, when ecosystems slowly reassembled from fragments, when plants spread across barren land and animals tested new forms. It was a world of strange reptiles unlike anything alive today, of amphibians clinging to survival, of insects buzzing through forests of cycads and conifers, of oceans learning to sustain life again. It was not the world of giant dinosaurs yet, but it was the foundation for everything that would follow. Walking through the Triassic in your mind, you would see landscapes raw and changing. You would breathe air heavy with volcanic gases in some regions, clearer others where forests had taken hold. You would see rivers cutting through deserts, their banks alive with amphibians and reptiles, while the deserts themselves stretched silent and empty. You would hear the calls of strange reptiles, the splash of marine creatures in shallow seas, the rustle of cycads in hot winds. It would be a world at once fragile and resilient, scarred but rebuilding, alive with the determination of survival. And this resilience is perhaps the key to understanding the Triassic. Life had been nearly erased, but it refused to end. Plants sprouted on bare ground, insects adapted to new diets, reptiles diversified into forms no one would have predicted. Out of catastrophe came renewal, and out of that renewal came the beginnings of the age of dinosaurs. When people think of dinosaurs, the mind usually leaps to the giants, the towering sauropods with their necks stretched toward the sky, or the massive predators with jaws that could swallow a person whole. But that's not how it began. The rise of the dinosaurs was not a sudden takeover, but a slow, steady climb from small, almost unremarkable beginnings. They started as little creatures that you might have overlooked if you were walking through the Triassic landscape, blending into the background among many other reptiles. Their story is one of persistence, of steady adaptation, and of opportunity seized when the moment finally arrived. At first, in the early Triassic, dinosaurs didn't even exist. The world was still dominated by other reptiles, particularly those related to crocodiles. These animals came in all shapes and sizes, some armored, some fast and agile, some aquatic, and some massive land predators. They filled many of the roles we might assume dinosaurs would have occupied, leaving the earliest dinosaurs to carve out small, unremarkable niches. When the first true dinosaurs appeared around 230 million years ago, they were neither dominant nor especially large. Most were no bigger than a dog or a person, two-legged animals with light skeletons and sharp teeth, adapted to catching insects or small prey. One of the earliest known dinosaurs, Euraptor, comes from what is now Argentina. It was a small, lightly built creature, probably less than a meter long, with grasping hands and a mouth lined with sharp teeth. It wasn't yet specialized, not a pure predator or herbivore, but something in between, feeding on whatever it could catch or scavenge. Another early dinosaur, Herrerasaurus, was larger, reaching up to 3 meters, and clearly a predator, with long legs for running and a flexible jaw lined with sharp teeth. These animals lived alongside many other reptiles that were not dinosaurs, and to someone observing the Triassic world, they wouldn't have stood out as the future rulers of the Earth. They were just part of the mix, survivors, in a landscape filled with experiments. What set dinosaurs apart, though, were a few key traits. Their posture was upright, with legs positioned directly under their bodies instead of sprawled to the sides like lizards or crocodiles. This made them efficient walkers and runners, able to move long distances without tiring. Their hips and joints were structured to support this stance, giving them a mechanical advantage that let them outcompete other reptiles in terms of mobility. Their lungs were likely more efficient, too, similar to modern birds, allowing them to draw more oxygen from each breath. These differences didn't make them dominant right away, but they gave them an edge that over millions of years would prove decisive. The Triassic landscape was one of extremes. Deserts stretched across much of the supercontinent of Pangaea, with oases of life along rivers and coasts. In these conditions, being small and mobile was an advantage. Dinosaurs, with their upright gait and light skeletons, could cover ground more efficiently than many competitors. They could survive in scattered environments, spreading slowly across regions. They weren't the top predators yet, but they were adaptable, and adaptability is often the key to long-term success. Over time, different branches of dinosaurs began to specialize. Some became more predatory, developing sharper claws, faster legs, and jaws designed for hunting. These would eventually give rise to the theropods, the group that included not just later giants like Allosaurus and Tyrannosaurus, but also much later birds. Others leaned toward herbivory, their teeth shifting to grind plants rather than tear flesh, their necks lengthening to reach higher vegetation. These would lead to the great sauropods of the Jurassic. Still others experimented with mixed diets and body forms, testing what was possible in this still recovering world. The real turning point came not because dinosaurs suddenly became dominant on their own, but because the world shifted around them. At the end of the Triassic, around 2 million years ago, another mass extinction struck. Massive volcanic eruptions split the supercontinent, releasing vast amounts of carbon dioxide and other gases into the air. Climate chaos followed. Oceans became unstable, and many of the dominant reptile groups that had held power through the Triassic collapsed. Crocodile relatives that had ruled the land were decimated. Amphibians lost much of their diversity. Ecosystems emptied again, leaving niches open. Dinosaurs, still small and varied but resilient, survived. And when the dust settled, they found themselves in a world with less competition. It was in the early Jurassic, after this extinction, that dinosaurs began their real rise. Freed from many rivals, they expanded rapidly, filling ecological roles across the continents. Herbivorous dinosaurs grew larger, evolving into the long-necked sauropods that grazed the tops of conifers and cycads. Predatory dinosaurs grew bigger and more specialized, becoming efficient hunters, capable of taking down large prey. New forms appeared in coastal and forested environments, diversifying in ways that other reptiles could not match. The small light-bodied survivors of the Triassic became the giants of the Jurassic, not overnight, but through steady steps taken over millions of years. This rise wasn't just about size. Dinosaurs developed new strategies for survival that helped them spread. Many laid eggs in nests and may have cared for their young, giving their offspring a better chance to survive. Some moved in herds, offering safety in numbers and greater efficiency in finding food. Their anatomy allowed for continuous growth, with some reaching sizes no other land animals could match. These behaviors and adaptations worked together, making them not just survivors, but dominators of ecosystems. It's easy to look back now and see inevitability in their rise, as if dinosaurs were destined to rule. But in their own time, their success was far from certain. They were just one branch among many, one set of reptiles trying their luck in a world reshaped by disaster. Their rise was not dramatic, but incremental, a series of small advantages that accumulated over tens of millions of years. Each step was modest: a slightly better lung, a more upright stride, a more versatile jaw. Each success was hard-won, the result of survival in harsh climates and unstable ecosystems. What made them giants later was not a single leap forward, but a long sequence of small steps that added up to dominance. Imagine standing in a Triassic forest as one of the first dinosaurs passes by. It wouldn't shake the ground or blot out the sun. It might only come up to your knee, moving quickly through the ferns, stopping to snap at an insect. Another slightly larger one might dart past, chasing after a lizard. You might not give them a second glance, compared to the armored reptiles grazing nearby, or the tall, massive predators stalking the rivers. And yet those small, lightly built creatures were the seeds of something vast, something that would stretch across the entire planet and last for more than 160 million years. Their story is a reminder of how evolution often works, not in sudden transformations or dramatic revolutions, but in steady shifts, tiny adjustments that over time reshape the possibilities of life. Dinosaurs did not rise because they were immediately superior, but because they were resilient, adaptable, and prepared to take advantage of change when it came. They were survivors first, giants later, and in the sweep of Earth's history, that patience made all the difference. The rise of the dinosaurs is in many ways a story of opportunity. They were not the rulers of the Triassic, not even close, but when catastrophe struck and the world reset, they were ready. The small steps they had taken, upright posture, efficient lungs, versatile diets, strong but light skeletons, suddenly became decisive advantages. From those modest beginnings came the giants that defined an entire era, their footsteps echoing across continents, their shadows stretching over forests, their presence shaping ecosystems from the ground up. And so when we think of the dinosaurs at their peak, we should remember where they started, small overlooked creatures in a world dominated by others. Their journey from those beginnings to the giants of the Jurassic was not a straight line, but a gradual climb. Each step mattered. Each adaptation carried them forward. Each survival bought them more time. They were not always giants, but they were always survivors. And in the end, survival was what allowed them to rise. By the time the Jurassic began, the Earth had been reshaped by loss. The Great Extinction at the end of the Triassic had cut down many of the dominant reptiles, leaving the landscape open for something new. The survivors of that event carried forward, and among them were the dinosaurs, still modest in size compared to what they would become, but already spreading across the continents. The stage was set for expansion, and what followed in the Jurassic was not a subtle rise but a transformation. The planet entered a period of warmth, greenness, and abundance, and in that setting, dinosaurs became not just survivors, but rulers. The Earth itself was shifting. Pangaea, the great superter continent that had defined the Triassic, began to break apart. Cracks opened, rifts stretched, and seas flooded into low areas, dividing what had once been one enormous landmass into smaller continents. With new coastlines came new climates. Rain fell in greater abundance, and the dry interiors of Pangaea gave way to wetter landscapes. Rivers carved through valleys, deltas spread across lands, and forests flourished in the improved conditions. The world of the Jurassic was greener, more hospitable, and more diverse than the one that came before it. This greenness provided food on a scale that the Triassic could not match, and the dinosaurs responded. Herbivorous dinosaurs grew to astonishing sizes, taking full advantage of the new abundance. Among them were the sauropods, the giants that came to define the Jurassic landscape. Creatures like Brachiosaurus and Diplodocus stretched their necks high into the canopy, or swept them low across plains, stripping vegetation with each movement. Their bodies were immense, their footprints leaving impressions large enough to hold pools of water after rains. Entire herds of these animals could move through a forest, consuming tons of plant matter each day, reshaping the vegetation around them. The size of these animals was unprecedented. No land creatures before or since have matched the sheer bulk of the largest sauropods. Some estimates suggest lengths of over 30 meters, and weights exceeding 70 tons. To stand near one would have been to feel small, in a way we can hardly comprehend today. And yet, they were not isolated giants. They lived in groups, moved together, and filled entire regions with their presence. The land was built to support them because the climate and vegetation allowed it. Without the warm, humid conditions of the Jurassic, without the sprawling forests of conifers, cycads, and ginkgos, such giants would never have been possible. Alongside the sauropods were other plant-eaters, of more modest size, but no less significance. Stegosaurs, with their double rows of plates and spiked tails, browsed on low vegetation, their armored backs, perhaps serving both for defense and display. Ornithopods, early relatives of the duck, built dinosaurs that would later dominate the Cretaceous, nibbled at plants with versatile jaws. These herbivores filled every niche from the ground level to the treetops, ensuring that no part of the vegetation was left untouched. And where herbivores thrived, predators followed. The Jurassic was home to formidable hunters, many of them theropods, the same lineage that would eventually give rise to birds. Allosaurus, perhaps the most famous of them, was a large predator that stalked the plains and forests of what is now North America. With sharp teeth and powerful jaws, it hunted in packs or alone, taking down prey much larger than itself. Other theropods filled roles from small insectivores to mid-sized hunters, creating a diverse predator community. These dinosaurs were fast, agile, and intelligent enough to track and bring down prey. Their success tied directly to the abundance of herbivores that surrounded them. The Jurassic skies were not empty. Pterosaurs, relatives of dinosaurs, though not true dinosaurs themselves, soared overhead. They had first appeared in the Triassic, but in the Jurassic they expanded into a variety of forms, some small and insect-hunting, others large enough to rival modern birds of prey and wingspan. Their presence added another layer to the ecosystem, feeding on fish along coastlines, hunting insects in forests, and sometimes scavenging from the kills of larger predators. The air was alive with their movements, a reminder that the age of reptiles extended into every environment. The seas of the Jurassic were equally full of life. Theosaurs, streamlined like dolphins, hunted in open waters. Plesiosaurs, with long necks and small heads, swam through shallows, their flippers propelling them with grace. Marine crocodiles prowled coastlines, their bodies adapted to life in the water. Fish schools darted in the shallows, ammonites floated in spiral shells, and reefs slowly rebuilt after their collapse at the end of the Permian. These oceans were not the same as ours, but were thriving ecosystems, part of the same greening, warming world that supported the land giants. The plants of the Jurassic were the silent partners in this story. Conifers dominated the forests, stretching high into the sky, their trunks wide and strong. Cycads dotted the plains, their thick leaves forming dense groves. Ginkgos spread their fan-shaped leaves across temperate zones. Ferns carpeted the undergrowth, and horsetails filled wetlands. Together, these plants produced the food and oxygen that sustained the age. The air itself was thick with their scents, resin, and spore, a reminder of the greenery that framed every dinosaur scene. The climate was a crucial factor in all of this. The Jurassic was warm, humid, and relatively stable. There were no permanent ice caps at the poles. Seasonal variation existed, but even in polar regions, forests grew, supporting dinosaurs that adapted to months of darkness without enduring freezing cold. Rainfall was abundant in many regions, feeding rivers and lakes that created fertile valleys. The greenhouse world of the Jurassic gave life room to flourish, and flourish it did, on a scale unmatched before or since. As continents drifted apart, the differences between regions increased. What is now North America was rich with floodplains and forests supporting vast herds of sauropods and their predators. Europe, broken into islands by rising seas, hosted smaller and more diverse ecosystems with unique dinosaurs adapted to limited spaces. Africa and Asia saw their own giants rise. Each continent developing a distinct community of species. Yet everywhere the pattern was the same: abundant vegetation, enormous herbivores, and powerful predators. What makes the Jurassic stand out in memory is the combination of size and scale. Dinosaurs had existed before, but in this era, they grew into the roles that would define them. They became the giants of the land, shaping ecosystems simply by moving through them. The world became one where their presence was undeniable, where no forest or plain could be imagined without them. They were not just animals in an ecosystem. They were the ecosystem, their grazing, trampling, and feeding shaping the land itself. The social lives of these creatures likely played a role in their success. Fossil evidence suggests some sauropods may have moved in herds, their young walking in the safety of the group. Their numbers are deterrent to predators. Stegosaurs may have used their plates for display as much as for defense, communicating with one another through sight as well as sound. Predators like Allosaurus may have coordinated their hunts, or at least tolerated each other long enough to feed together on a kill. These behaviors hint at intelligence and complexity, qualities that would help them adapt to a dynamic world. In imagining the Jurassic world, you have to think not just of the animals, but of the constant motion of the environment. Herds of sauropods moving across plains, predators following at a distance, pterosaurs circling overhead, ferns crushed beneath feet, rivers swollen with seasonal rains. The soundscape would have been immense. Calls echoing through forests, the splash of marine reptiles along coasts, the crash of trees pushed aside by giants, the constant background of insect life buzzing through the greenery. It was a living, breathing planet, filled with movement at every level. And through all of this, the dinosaurs secured their place. They had risen from small beginnings in the Triassic, but by the Jurassic, they were the undisputed rulers of the land. Their success was not just in their size, but in their adaptability, their diversity, and their ability to thrive in every environment the changing Earth offered. They were not yet at the peak of their diversity that would come later in the Cretaceous, but they had achieved something new: dominance, on a scale the world had never seen. The Jurassic world was green, fertile, and full of great beasts. It was a time when the Earth itself seemed to conspire in their favor, offering climates and vegetation that allowed them to flourish. To walk in that world would have been to walk in a landscape defined by dinosaurs not as curiosities or scattered survivors, but as the foundation of life itself. Among all the animals that ever walked the Earth, none captured scale the way the great sauropods did. When people picture dinosaurs, they often imagine towering necks rising above forests, tails sweeping across plains, and bodies so immense that the ground seemed to tremble beneath them. These were the titans of the Jurassic and Cretaceous, a lineage that stretched across millions of years and countless continents. Their rise was not sudden, but built upon the opportunities of a warming green Earth, and once they appeared, they grew into shapes and sizes that still challenge imagination today. The sauropods began as modest creatures in the Triassic, small, lightly built animals, not so different from other plant-eaters of their time, but their anatomy carried hints of what was to come. Their necks were already lengthening, their skeletons already lighter than expected for their size, their limbs strong and straight like columns. They were built for growth, for expansion, for reaching into niches no other land animal could touch. By the Jurassic, these features had come together in a way that made them unstoppable. The environment provided what they needed. Forests of conifers, schizicids and ginkgos stretched across the land, producing abundant food. Warm climates, with high carbon dioxide levels, encouraged rapid plant growth, creating ecosystems rich in vegetation. Rivers and floodplains sustained endless groves of greenery. In this world, an animal that could process enormous quantities of plants had a tremendous advantage. The sauropods answered that call. Their long necks let them feed across wide ranges without moving much. Their peg-like teeth stripped foliage efficiently, and their huge digestive systems extracted what energy they could from tough plant material. They were not selective eaters, but bulk feeders, designed to consume in volume rather than precision. Their size was not simply indulgent. Being enormous brought survival advantages. Predators. Even the largest theropods of the Jurassic, like Allosaurus, would have thought twice before attacking a fully grown sauropod. Size itself was a defense, making them nearly untouchable as adults. Their height gave them access to food that no other herbivore could reach, allowing them to browse above the level of stegosaurs or smaller ornithopods. Their mass helped them retain heat, making them stable in varying climates. Growth itself became a strategy, pushing them into a realm where few threats could follow. The engineering of their bodies was remarkable. Their bones were not solid, but filled with air spaces, reducing weight while maintaining strength. Their long necks were supported by an intricate system of muscles and ligaments, with vertebrae shaped to lock together efficiently. Their lungs were likely bird-like, with air sacs extending through the body, keeping oxygen flowing and cooling their massive frames. Their legs were thick and straight, like pillars, distributing weight evenly across joints and bones. Every part of their anatomy was tuned towards sustaining immense size, an evolutionary experiment pushed to its extreme and proven successful for tens of millions of years. Different lineages of sauropods adapted to different strategies. Some, like Brachiosaurus, held their necks upright, browsing high into the canopy, feeding on branches that no other herbivore could touch. Others, like Diplodocus, extended their necks horizontally, sweeping across low vegetation, clearing vast swaths with little effort. Some developed whip-like tails that may have served as defense, communication, or even sonic weapons, snapping with enough force to create sound. The variety of shapes reflected the variety of environments, each species carving out its place in the green abundance of the Jurassic and Cretaceous world. The presence of these giants shaped the ecosystems around them. Entire forests may have been structured by their feeding habits, with vegetation adapted to constant grazing. Their movements across landscapes, trampled plants, carved paths, and redistributed nutrients. Their dung fertilized soils, sustaining insect populations, and cycling nutrients through ecosystems. To imagine the Mesozoic without sauropods is impossible. They were engineers of the land, their sheer existence reshaping the planet. Despite their size, they began life small. Fossil nests reveal that sauropods laid eggs, often in large numbers, each egg no bigger than a grapefruit or soccer ball. The young that hatched were tiny compared to their parents, vulnerable to predators of all kinds. Survival rates were low, but those that made it grew quickly, some species doubling in size within their first year. Rapid growth was essential, carrying them out of the dangerous small animal stage and into the safety of size. Herd behavior may have helped with groups of adults protecting the young, or at least overwhelming predators through sheer numbers. In this way, the cycle of vulnerability and survival carried the lineage forward. Predators adapted as well. While adult sauropods were nearly invulnerable, juveniles were frequent targets. Packs of theropods may have coordinated to harass or separate young from herds, taking advantage of any weakness. Some fossil evidence suggests tooth marks on sauropod bones consistent with repeated attacks, perhaps even scavenging on the carcasses of the immense animals. This arms race between predator and prey was part of the balance of Jurassic life, though it was a balance weighted heavily in favor of the giants once they reach maturity. The global spread of sauropods speaks to their success. Fossils have been found on every continent, from North America and Europe to Africa, South America, and Asia. Even Antarctica, during the warmer Mesozoic, hosted their remains. Their adaptability let them thrive in a variety of environments, from lush river valleys to drier plains. They were not confined to one region or one climate, but expanded wherever vegetation could sustain them. Their shadows stretched across the entire Earth. As time went on, sauropods continued to diversify. In the Cretaceous, groups like the Tyrannosaurs took over, evolving new forms that carried their lineage to the very end of the age of dinosaurs. Some Tyrannosaurs were even larger than their Jurassic ancestors, pushing the limits of size further. These animals walked among flowering plants that had begun to spread, sharing the world with new forms of dinosaurs that had risen during the Cretaceous. Even as ecosystems changed, the sauropods remained, their formula of size and adaptation continuing to work. Their extinction at the end of the Cretaceous was not a failure of design, but a consequence of catastrophe. The asteroid impact and the volcanic eruptions of the Deccan traps transformed the world in ways no animal could withstand. The giants that had survived and thrived for over 100 million years were undone by forces beyond adaptation. And yet in their time, they were unmatched living monuments to what evolution could achieve. To imagine standing among them is to confront scale itself. A diplodocus sweeping its neck across a plain, a brachiosaurus reaching high into the canopy, a herd of Argentinosaurus moving slowly across a valley, their bodies blotting out the horizon. The ground would have shaken with each step, the air filled with the sounds of their movements, the landscape dominated by their presence. They were not simply animals in their environment, they were the environment shaping everything around them through size alone. Even today, their legacy lingers. Birds, distant relatives within the dinosaur lineage, carry echoes of sauropod lungs and bone. Structures, fossilized footprints preserved in stone, capture the weight of their steps and the paths of their herds. The very idea of giants of creatures, so vast they defy comprehension, remains tied to their image. They were the titans of Earth, and their shadows still stretch across imagination. Their story is one of extremes of biology, pushed to its limits and sustained by the balance of climate, vegetation, and anatomy. They remind us of what the world can produce when conditions align. When abundance allows for growth on a scale beyond what seems possible in their time, they were not marvels, but normal, part of everyday life on a green Earth. It is only from our perspective looking back across millions of years that they seem extraordinary. And as the Jurassic world carried forward, the presence of these titans set the stage for everything else. Their shadows stretching across ecosystems, their bodies defining the scale of life itself. Predators have always held a particular fascination in any age of life on Earth, and in the time of the dinosaurs, they were both the balance and the threat that shaped everything around them. For every herd of sauropods moving through a valley, for every stegosaur grazing in the shade of cycads, there was a hunter watching, waiting, or simply surviving on the opportunities that a world of giants could offer. These hunters were not all the same, not all massive and terrifying like the creatures that make their way onto movie screens. They range from quick-footed insect chasers, barely taller than a person's knee, to apex predators capable of bringing down prey many times their size. Together, they created a spectrum of carnivores, each adapted to a role in the dynamic ecosystems of the Jurassic and Cretaceous, each leaving behind a mark in the fossil record that tells us about the endless strategies of survival. The earliest theropods, the branch of dinosaurs that included all the meateors, had already appeared back in the Triassic. They were small then, more opportunists than kings of the land, living in a world still dominated by crocodile relatives. By the Jurassic, however, the picture was different. With the extinction that closed the Triassic, having cleared away so many competitors, theropods stepped into open space and diversified. They did not all immediately grow huge, but they expanded into every available role. Some remained small, focusing on insects, lizards, or carrion. Others grew into medium-sized predators, quick enough to chase ornithopods or juvenile sauropods. Still others pushed upward into the ranks of the large carnivores, their bodies built for power, their teeth sharpened for flesh. Among the most famous of these was Allosaurus. Known from fossils in North America, Allosaurus was large, but not the largest of predators, about 8 to 10 meters long on average. What made it formidable was not just size, but design. Its skull was filled with sharp serrated teeth, suited for slicing flesh. Its arms, though shorter than its legs, ended in three-fingered hands, tipped with strong claws. Its legs were powerful, built for running bursts of speed. Fossil evidence suggests it was an active hunter, capable of taking on large prey, perhaps even working in loose groups to bring down sauropods. If you imagine a scene where a herd of Diplodocus is passing across a plain, you might also picture Allosaurus trailing along, watching for the moment when a young or weakened member strayed just far enough from the safety of the herd. But Allosaurus was not alone. Across the Jurassic world, theropods of many shapes filled similar niches. In Africa, creatures like Ceratosaurus prowled the floodplains. With a distinctive horn on its snout and blade-like teeth, it was well suited to hunting along rivers and lakes, perhaps ambushing prey that came to drink. In Europe, Megalosaurus, one of the first dinosaurs ever named in scientific history, lived during the Jurassic, a mid-sized predator in forests that were broken into islands by shallow seas. Each region had its apex hunters, distinct in form, but united by their role. The smaller predators were just as important. Chilophosis, for example, was a slender, lightly built dinosaur that hunted in packs during the late Triassic and into the early Jurassic. It wasn't large, just a few meters long, but in numbers, it could overwhelm prey. Its agility allowed it to dart after lizards and insects, filling a niche far from the world of the sauropods. Later comes nothing, tiny theropods no bigger than a chicken, skewered through undergrowth, feeding on insects and small vertebrates. They were reminders that not every predator of the age was a terrifying giant. Most were small, quick, and opportunistic. This range of predator sizes created a layered system, much like ecosystems today. Large hunters controlled populations of big herbivores. Medium-sized predators focused on smaller prey, and the smallest scoured the landscape for whatever could be caught. It was a dynamic balance, with competition not only between predator and prey, but between predators themselves. Allosaurus, for example, may have clashed with Ceratosaurus in regions where their ranges overlapped, competing for access to carcasses or hunting grounds. Smaller theropods had to navigate around these giants, avoiding becoming prey themselves. Hunting strategies varied as well. Some dinosaurs were ambushers, relying on camouflage and sudden bursts of speed. Others were pursuit hunters, built to run prey down over longer distances. Some may have scavenged as much as they hunted, using keen senses to locate carcasses left behind by others. The debate about whether large predators like Allosaurus were primarily hunters or scavengers reflects this complexity, but in reality, most likely did both. In nature, energy is precious, and no opportunity would have been ignored. What these hunters shared was a constant dependence on the herbivores around them. Without the massive herds of sauropods, stegosaurs, and ornithopods, there would have been no ecological room for the great carnivores. Their lives were tied to the rhythms of their prey, following migrations, waiting at water sources, or trailing herds. Each kill provided not only for the hunter, but for an entire ecosystem of scavengers, from smaller theropods to mammals, insects, and even plants nourished by the nutrients returned to the soil. Predation was not just violence. It was a cycle that sustained the balance of life. In the Cretaceous, the diversity of predators expanded further. New lineages rose, some reaching even greater sizes than their Jurassic predecessors. Spinosaurus, with its elongated jaws and sei-like back, prowled the rivers of what is now North Africa, hunting fish and perhaps scavenging along the shores. Its body was adapted for a semi-aquatic lifestyle, making it unique among the great theropods. In Asia, Tarbosaurus, close relative to Tyrannosaurus, ruled the late Cretaceous landscapes. Its massive skull and powerful bite adapted for crushing through bone. In South America, Giganotosaurus reached lengths comparable to or even exceeding Tyrannosaurus. part of a group of massive predators that thrived in southern continents. The variety of forms showed how adaptable predators could be. Some specialized in certain prey or habitats, like fish-eating spinosaurids or fleet-footed raptors that hunted in packs. Others remained generalists, capable of taking whatever opportunities arose. This adaptability was one reason theropods lasted so long, surviving multiple extinctions and diversifying into new forms, including eventually the birds that still live today. The relationship between predators and their environment went beyond hunting. Fossil trackways show evidence of movement patterns, with groups of carnivores following and herds of herbivores, leaving footprints preserved in mud that hardened over millions of years. Bite marks on bones reveal failed hunts, injuries that healed, or deaths that fed others. Even the distribution of fossils reflects predator behavior, with bone beds sometimes containing multiple individuals of the same species, suggesting group living or shared feeding grounds. For the smaller hunters, survival was a daily challenge. They had to avoid larger predators while still finding enough food to sustain themselves. Some evolved feathers not for flight, but for insulation or display, hinting at the evolutionary path that would eventually lead to birds. Feathers may have given them camouflage, or a way to signal to others in social groups. The smallest predators remind us that evolution was never only about size. It was about finding workable solutions to the pressures of survival. To imagine a day in the life of these hunters is to picture constant motion. A large predator might spend hours stalking a herd, waiting for weakness to show, while scavenging smaller kills along the way. A small predator might scurry through underbrush, catching insects or stealing from nests, always alert for larger threats. The air might be filled with the calls of pterosaurs circling above, hoping to claim scraps from a kill, while mammals darted in to feed on leftovers when the giants had moved on. Every size, every shape had its place, each predator tied to a role that maintained the rhythm of the age. Their legacy is not just in bones and teeth, but in the reminder that life adapts to fill every niche. For every towering sauropod, there was a hunter capable of testing its defenses. For every insect hiding in the foliage, there was a tiny predator seeking it out. The Mesozoic was not a world of unchecked herbivores or lonely giants, but of balances, tensions, and interactions that created the richness of ecosystems. Predators were the sculptors of this balance, ensuring that populations did not overwhelm landscapes, keeping the cycle of life turning across millions of years. And so, in the great sweep of the Mesozoic, the hunters were always there, from the small and nimble to the massive and powerful. They were the watchers in the shadows of forests, the chasers across plains, the scavengers along rivers, and the opportunists that never let a meal go to waste. They remind us that dominance comes in many forms, not only in size, but in persistence, adaptability, and the ability to live in the spaces left open by others. When we picture the Mesozoic, it's tempting to think of it as a world ruled only by giants on the ground, herds of sauropods crossing valleys, and predators stalking their every move. But if you tilted your head back and looked up, the skies were no less alive. Long before birds as we know them appeared, the air belonged to other reptiles, the pterosaurs, who spread their wings over oceans, forests, and plains. They were not dinosaurs, though they shared a common ancestry with them, but their story is woven tightly into the same age. They represent another way life stretched into possibility, taking a step no land vertebrate had taken before them. Powered flight. The first pterosaurs emerged in the late Triassic, small creatures with wings, supported by a single elongated finger. Imagine your own hand with one finger stretching impossibly long, skin and muscle extending from it down to your body, creating a surface to catch the air. That was the basic structure of the pterosaur wing, where dinosaurs had legs beneath them to conquer the land. Pterosaurs reshaped their anatomy to master the sky. Their bones were light and hollow, their muscles arranged for powerful flapping. Even the earliest of them could glide and maneuver, hunting insects or small prey in ways no other animal of their time could. By the Jurassic, they had spread into many forms. Some were small, little more than the size of sparrows, darting through the air after insects. Others grew larger, wings stretching several meters, their long jaws snapping at fish as they skimmed over lakes and seas. The variety was astonishing. Some had long tails with diamond-shaped veins at the tip, perhaps for stability and flight. Others shortened their tails and grew elaborate crests on their heads, which may have been used for display, signaling, or balance. They were as diverse in the sky as dinosaurs were on the ground, filling niches from insect eaters to fishes to scavengers. The oceans, in particular, offered enormous opportunity. Many pterosaurs evolved long pointed jaws, lined with interlocking teeth, perfect for catching slippery fish. Fossils show species like Rampincus, with wings adapted for gliding over water. Their sharp teeth ideal for snapping prey from below the surface. They may have filled a role similar to modern seabirds, following schools of fish, nesting along cliffs and feeding in groups. The sight of dozens of pterosaurs circling above waves, diving and skimming, would have been as familiar then as seabird colonies are today. On land, other species adapted to different diets. Some likely fed on small vertebrates, lizards, or even carrion. Their sharp eyesight would have made them excellent hunters, scanning the ground from above for any movement. Some may have been opportunists, swooping down on the remains left behind by larger dinosaurs. The diversity of wing shapes and body sizes tells us they were not confined to a single way of life, but explored many options, just as mammals and birds do today. As time passed, pterosaurs grew larger. By the late Jurassic, wingspans of over 10 meters were possible. By the late Cretaceous, creatures like Quetzalcoatlus reach sizes that still strain belief. With wings stretching 12 meters across, taller than a giraffe when standing on the ground, these were the largest flying animals to have ever lived, using air currents and soaring techniques to cover vast distances. They were not delicate gliders, but strong, capable flyers, landing on the ground to stalk prey with long stalk-like legs, then launching into the air again with powerful wing beats. Their success was extraordinary, lasting for over 150 million years. They were the undisputed rulers of the sky during the Mesozoic, but they were not alone there. During the Jurassic, another experiment in flight began, one that would carry forward into our own age. The first birds. The line between small theropod dinosaurs and early birds is blurred. Dinosaurs like Microaptor and Anornis had feathers, wings, and the anatomy necessary for gliding or limited flapping flight. They were not quite birds as we think of them, but they were close. Feathers themselves had appeared earlier, not originally for flight, but likely for insulation or display. Over time, they became more elaborate, forming structures that could catch air. Evolution often works this way, repurposing what already exists for new functions. And in this case, it transformed a covering for warmth into the machinery of flight. The most famous of these early birds is Archoprick, from the late Jurassic of what is now Germany. Its fossils are iconic, preserving feathers in exquisite detail. It had wings and feathers like a bird, but also teeth, claws on its wings, and a long bony tail like a dinosaur. It was a mosaic of traits, partway between its theropod ancestors and the birds that would follow. Archoprick could likely glide and may have managed powered flight for short distances, hopping between trees or escaping predators by taking to the air. It was not yet the master of flight that modern birds are, but it was a beginning. The forests of the Jurassic would have been alive with these experiments. Small feathered dinosaurs clambering up trees, launching themselves into the air, gliding down to the forest floor or across clearings. Pterosaurs soaring above open landscapes, casting shadows over herds below. The air was becoming a frontier of its own, not empty, but crowded with life testing the possibilities of wings. Each lineage found its way, sometimes overlapping, sometimes dividing the sky into separate domains. Birds and pterosaurs were not direct competitors in every case, as their diets and sizes often differed, but their coexistence must have created some tensions, so both relied heavily on fish, insects, and small prey. In coastal regions, colonies of pterosaurs may have shared cliffs with early birds, each species taking its share of food. Some smaller birds may have darted into niches that larger pterosaurs ignored, while pterosaurs dominated in sheer scale. For millions of years, they lived side by side, the air alive with both groups. Flight itself carried advantages beyond food, the ability to escape predators, to cover distances quickly, to colonize new habitats. All of these gave flyers unique resilience. If food grew scarce in one area, they could travel to another. If predators prowled below, they could take to the air. This mobility helped them spread across continents, ensuring survival even in changing climates. The development of flight also reshaped behavior. Nesting strategies changed, with some species likely laying eggs on cliffs or high in trees, safe from ground-based hunters. Social behavior may have evolved, with groups flying together for safety or efficiency. Vocalizations may have become more complex as communication in the air carried new importance. The Mesozoic sky was not silent. It would have been filled with cries, calls, and the rush of wings, adding another layer to the soundscape of the age. By the Cretaceous, birds were diversifying rapidly. They began to lose teeth, their tails shortened into the compact structure of modern birds, their wings refined for more efficient flight. Some became specialized divers, others perching insect eaters, others strong flyers, capable of crossing long distances. They were still living in the shadow of pterosaurs, but they were expanding steadily, laying the foundation for the explosion of bird diversity that would follow the end of the dinosaurs. Meanwhile, pterosaurs continued to innovate. Some developed elaborate head crests, possibly for species recognition or mating displays. Others refined their wings for different styles of flight, from soaring to maneuvering in dense forests. They were not static creatures, but evolving, responding to pressures just as birds did. For much of the Mesozoic, they remained dominant in the skies, unmatched in size and diversity. The eventual disappearance of pterosaurs at the end of the Cretaceous was not because they were inferior, but because the same catastrophe that ended the non-avian dinosaurs reshaped the entire planet. Birds smaller and more adaptable survived and carried flight into the new age. But during the long stretch of the Mesozoic, it was the pterosaurs who first showed what powered flight could achieve, and the earliest birds who hinted at what it would one day become. Looking back, the awakening of the sky during the Mesozoic is as dramatic as the rise of dinosaurs on land. In just a few tens of millions of years, Earth went from a world where nothing larger than an insect could truly fly, to one where the skies were crowded with winged reptiles and feathered to dinosaurs. It was a transformation that redefined ecosystems, opening a new frontier that remains central to life today. The air, once empty, became a place of hunting, travel, and communication as vital as land or sea. To imagine standing on a Jurassic plain and looking up is to see movement everywhere. Pterosaurs circling, wings casting shadows, some diving toward rivers for fish, small feathered dinosaurs gliding between trees at the forest's edge, the cries of early birds mixing with the rasping calls of pterosaurs, the air itself filled with life. It was not quiet, not empty, but a realm as full and diverse as the land below. And as the Mesozoic continued, the balance between these sky dwellers shifted. Pterosaurs remained giants of the air until the very end, but birds were steadily refining, building toward their eventual dominance. Together, they remind us that the story of life is not only told on the ground, but in every space Earth allows. That the sky was as much a stage of the age of dinosaurs as the forests and oceans beneath it. If you could stand on the shore of a Jurassic or Cretaceous sea, you might think at first that it looked familiar. Waves rolling in, sandy beaches stretching, the cry of winged creatures overhead. But if you peered beneath the surface, you would find a world entirely different from the oceans we know today. It was a world dominated not by whales or dolphins, because those wouldn't appear for tens of millions of years, but by reptiles. While their cousins ruled the land and others soared through the air, here in the sea were creatures that looked like dragons, serpents, and fish all at once. They were not fish, and they were not dinosaurs, but marine reptiles, a group of lineages that adapted to life in water with such success that they became the undisputed rulers of the ancient seas. The first of these were Dinosaurs. Their story began in the Triassic, when some reptiles took to the water after the devastating extinction that ended the Permian. Over time, they became streamlined, their bodies shaped like modern dolphins, though their ancestry was very different. Ichthyosaurs had long snouts filled with sharp teeth, perfect for catching fish and squid. Their eyes were enormous, some of the largest ever found in any animal, giving them excellent vision in deep or dim waters. Their fins were broad and paddle-like, their tails forked, built for speed. In the early Mesozoic, they were among the top predators of the seas, chasing prey through shallow oceans and leaving behind skeletons that show how fully adapted they became to a life they would never leave. By the Jurassic, Dinosaurs had diversified into many forms. Some were sleek hunters built for speed, while others grew to colossal sizes, rivaling whales in length. Fossils of Chaosaurus, for instance, suggest animals over 15 meters long, vast bodies moving through ancient waters. These giants fed on schools of fish and sauropods, filling the role that blue whales occupy today. Others specialized in smaller prey, darting after squid with agility. The variety of their body shapes and sizes shows how flexible their design was, how well it fit the world of the time. Perhaps most extraordinary is the ways gave birth. Unlike most reptiles that laid eggs on land, ichthyosaurs bore live young directly into the water. Fossils preserved mothers, with embryos still inside, or even caught in the act of giving birth. This adaptation freed them entirely from the land, allowing them to spend their entire lives at sea. It's one of the clearest signs that they were not temporary visitors, but permanent residents of the ocean. Sharing the seas with them were the plesiosaurs, another lineage of marine reptiles that first appeared in the Triassic, but became especially diverse in the Jurassic and Cretaceous. Their body plan was unlike anything alive today. They had broad, flat bodies, short tails, and 4 long flippers that propel them through the water with powerful strokes. Some, the long-necked plesiosaurs, stretched their necks into astonishing lengths with dozens of vertebrae, creating a flexible appendage that could snake through schools of fish or probe into tight spaces. Their heads were small compared to their bodies, their teeth needle-like, perfect for catching slippery prey. Imagine a creature like a Lasmosaurus, with a neck so long it accounted for more than half its total length. It swam with grace, its flippers moving in synchronized motions, almost like the wings of a bird underwater. With such a long reach, it could keep its bulky body hidden below while extending its head forward to snap at fish, squid, or anything small enough to swallow. To modern eyes, they look almost fantastical, like something from a myth, but their fossils are abundant, leaving no doubt that they were real and widespread. Other plesiosaurs, the pliosaurs, took a different path. Instead of long necks, they developed short muscular ones and massive heads filled with large conical teeth. These were the apex predators of their time, built less for delicate fishing and more for raw power. Creatures like Kronosaurus or Leo's pleurodon could reach lengths of 10 to 12 meters, their jaws capable of seizing not just fish, but other marine reptiles. They were the top hunters of the oceans, their sheer presence dominating the food chain. A plesiosaur waiting an ambush would have been a terrifying sight, a reminder that the seas of the Mesozoic had dangers as great as any on land. As the Jurassic gave way to the Cretaceous, a new group rose to prominence, the mosasaurs. They were later rivals, not appearing until the mid-Cretaceous, but when they did, they rapidly became the dominant marine predators. Unlike ichthyosaurs or plesiosaurs, mosasaurs were closer relatives of modern lizards and snakes. They had long muscular bodies, powerful tails, and limbs modified into flippers. Their skulls were flexible, with double-hinged jaws much like snakes, allowing them to swallow large prey. Some species grew to lengths exceeding 15 meters, making them the undisputed rulers of the late Cretaceous seas. Mosasaurs were versatile hunters. Some fed primarily on fish and squid. Others specialized in hard-shelled prey, like ammonites and turtles, crushing them with robust teeth. The largest of them hunted anything they could overpower, including other mosasaurs. Fossil evidence shows stomach contents that include birds, marine reptiles, and large fish, suggesting a diet as broad as their reach. They swam with powerful side-to-side motions of their tails, gliding with efficiency, but capable of bursts of speed when needed. Their rapid rise and dominance speak to their adaptability, and they became widespread across the globe. From shallow coastal seas to deeper waters, the oceans of the Mesozoic were not just home to these giants, but teeming ecosystems filled with other life. Ammonites with their coiled shells floated through the water like nautiluses, some small, others the size of car tires, their shells patterned with intricate sutures. They were prey for many marine reptiles, but also major players in their own right, forming vast swarms that fed the seas. Beamnites, squid-like creatures with bullet-shaped internal shells, darted through the waters, another staple in the diet of predators. Reefs grew from corals, though different from those we know today, providing shelter for fish and invertebrates. Sharks swam in numbers already ancient by this time, and rays glided across sandy bottoms. The seas were busy, layered worlds, with creatures of every size moving through the currents. Life in these oceans was not without danger. The balance between predator and prey meant constant struggle. A school of fish might be torn apart by athosaurs. A plesiosaur's long neck might snake silently toward a squid. A mosasaur might rise from below, jaws opening wide to engulf a turtle. For every creature, survival depended on vigilant speed and often sheer luck. The fossil record captures this drama in frozen moments. Bones of prey inside predators, tooth marks gouged into shells, ammonite shells cracked and crushed. They are reminders that the seas, though beautiful, were filled with relentless conflict. What is striking about these marine reptiles is how completely they adapted to environments so different from the land where their ancestors once walked. They developed flippers, streamlined bodies, new ways of breathing and reproducing, even specialized senses. Each group, ichthyosaurs, plesiosaurs, mosasaurs, took its own path into the water, yet all achieved dominance for millions of years. Their stories are parallel experiments in evolution, each showing how life reshapes itself to new opportunities. And while they dominated, they were also part of the larger world. Pterosaurs circled above, diving for fish. Dinosaurs came to the shores, perhaps scavenging beached carcasses. The climate and geography that shaped life on land shaped the seas as well, with continents splitting and oceans opening, currents changing, coastlines shifting. The marine reptiles were tied to these changes, their diversity rising and falling with the fortunes of the earth itself. Their eventual decline came at different times. Ichthyosaurs faded before the end of the Cretaceous, their diversity dropping sharply as climates changed and competition increased. Plesiosaurs lasted longer, some surviving until the final extinction event. Mosasaurs, the latecomers, thrived until the very end, disappearing only when the asteroid, impact and subsequent global upheavals wiped out most of the large reptiles. It was not failure that ended them, but catastrophe, the same sudden violence that ended the reign of the dinosaurs on land. To picture the Mesozoic oceans is to see movement and power on a grand scale. Imagine standing on a cliff and looking down into clear water, seeing the shadow of an ichthyosaur speeding below, or the long neck of a plesiosaur winding through the waves. Imagine the splash of a mosasaur breaking the surface as it lunged for prey, its jaws closing with enough force to crush bone. These seas were not empty expanses, but realms filled with life, as rich and dramatic as the forests and plains of the time. Even today, the traces of these creatures linger. Their fossils, sometimes complete with outlines of skin or stomach contents, tell us about their lives. Their shapes inspire myths of sea serpents and dragons, echoes of a time when reptiles ruled, not just land and air, but water as well. And their story reminds us that no realm of Earth was untouched during the age of reptiles, that the Mesozoic was as much an age of seas as it was of dinosaurs. The ocean in that era was alive in ways hard to overstate. Every current carried predators and prey. Every reef bustled with activity. Every deep water held giants. To think of the Mesozoic without them is to miss half the story, because these seas were not just background, but the stage for their own dramas parallel to those on land. They were alive with ichthyosaurs, plesiosaurs, and mosasaurs, each carving their place in history, each proof of how life can thrive in any corner the planet allows. If we think of the Mesozoic only as the age of dinosaurs, we miss the deeper forces that allowed it all to happen. Beneath the forests and the seas, beneath the herds of sauropods and the soaring pterosaurs, the planet itself was shifting slowly but relentlessly. Continents that had once been fused together as one vast supercontinent began to crack apart, splitting into smaller pieces that drifted across the surface of the globe. Mountains rose, oceans opened, climates changed, and with each alteration, ecosystems were reshaped. The creatures we've spoken of did not live in isolation, but on a planet always in motion, and that motion determined what thrived, what vanished, and what evolved in between. At the dawn of the Triassic, the Earth's landmasses were joined together in Pangaea, a supercontinent stretching from pole to pole. Imagine a single giant landmass, deserts spreading across its vast interior, coastlines ringing its edges, and mountains scattered like seams where continents had collided. It was a world both unified and extreme. The central regions of Pangaea were arid, far from the moderating effects of oceans, while the coasts supported more temperate climates. Life after the Great Permian Extinction had to spread across this vast surface, finding niches in environments that range from dry plains to lush coastal forests. As the Triassic gave way to the Jurassic, Pangaea began to break apart. Great rifts split the land, pulling continents slowly away from each other. These rifts filled with seas, forming new coastlines. The Atlantic Ocean, narrow at first, began its long, widening journey. Africa, South America, North America, and Europe were gradually pried apart. The Indian subcontinent, once connected to Africa, would in time drift away entirely. Australia and Antarctica, still joined then, sat closer to the pole. It was not a sudden transformation, but a slow rearrangement so gradual that no creature could notice in its own lifetime. But across millions of years, the face of the Earth was entirely altered. The splitting of continents created new opportunities where rifts opened. Shallow seas formed, filled with marine life, attracting predators and prey alike. New coastlines meant new habitats for plants and animals. Isolation of land masses encouraged divergence, species evolving differently as they were cut off from one another. What had once been a single interconnected world began to fragment, and that fragmentation drove diversity. Dinosaurs that spread across Pangaea in the Triassic began to branch into distinct lineages on separate continents by the Jurassic and Cretaceous. Mountains grew in this time as well. The collision of tectonic plates forced land upward, creating ranges that altered weather patterns and provided barriers to movement. In what is now western North America, the beginning of mountain building during the Jurassic and into the Cretaceous created landscapes that would later become the Rocky Mountains. These uplifts shaped rivers, directed rainfall, and created basins where sediments gathered. preserving the fossils that tell their stories today. In South America, the Andes would not fully rise until later, but tectonic movements were already reshaping the region. In Eurasia, collisions between landmasses pushed up mountains that influenced climates across vast areas. Each rise of land altered the flow of air and water, creating rain shadows, shifting winds, and redirecting ecosystems. Mountains were not just backdrops, but engines of environmental change. The shifting continents also changed the oceans. When land masses moved apart, currents were altered, circulation redirected. Warm water flowed into new regions, cooling in others. This reshaping of currents affected climate globally, influencing rainfall, temperature, and even the distribution of oxygen in the seas. Marine reptiles, ammonites, and fish adapted to new patterns of nutrient flow, some flourishing in newly opened seaways, others declining as conditions shifted. One of the most dramatic consequences of shifting land was the creation of seaways that split continents into smaller regions. During the Cretaceous, high sea levels flooded low-lying areas, creating shallow inland seas. North America was split in two by the Western Interior Seaway, stretching from the Gulf of Mexico to the Arctic Ocean. This vast body of water teemed with mosasaurs, plesiosaurs, and schools of fish, its shores lined with dinosaurs that roamed what land remained. To stand in central North America during the Cretaceous would have been to stand on the edge of a shallow sea, waves lapping, where today there are prairies. These seaways acted as both barriers and highways. They prevented some animals from crossing, isolating populations and promoting new species, while also allowing marine creatures to spread across continents. They turned inland regions into coastal ones, filling them with new life. Entire ecosystems depended on these seas, and when they retreated, they left behind layers of sediments rich with fossils, preserving a record of the creatures that swam within them. As continents drifted, climates shifted as well. Regions that had once been humid became arid, deserts forming where rain no longer fell. Others grew wetter as mountains captured moisture-laden winds. Tropical belts shifted with the tilt of the continents, spreading lush vegetation into new areas. Dinosaurs adapted to these changes, some thriving in forests, others in open plains. Plants evolved too, with flowering plants appearing in the Cretaceous, altering the diets of herbivores and changing the shape of landscapes. The scale of time involved makes it difficult to grasp for us. Continents seem immovable, mountains eternal. But in the Mesozoic, as in all eras, the Earth was alive with geological motion, plates grinding slowly but inevitably across the globe. In 1,000,000 years, a coastline shifted. In 10 million, an ocean opened. In 50 million, a mountain range rose from flat land. Each change altered climates, ecosystems, and the course of life. Evidence of these shifts lies in the rocks themselves. Sedimentary layers record the rise and fall of seas, volcanic rocks, the outpouring of molten material at rift zones. Fossils found in one region match those across oceans, proof that the land was once joined. Paleomagnetic signatures in rocks reveal the drift of continents, showing how they moved over time. The Earth's surface is a record of motion written slowly but legibly for those who learn to read it. For the creatures alive, then these changes were both opportunities and challenges. A herd of herbivorous dinosaurs might find new grazing grounds as climates grew wetter, but might also face extinction as habitats dried. Marine reptiles flourished in new seas, but perished when currents shifted. Isolation created new species, but also trapped others in shrinking habitats. The patterns of change were both creative and destructive, as relentless as the grinding of the plates themselves. Volcanoes added their own influence. The breaking of continents was often accompanied by vast volcanic activity, pouring lava across landscapes, releasing gases into the atmosphere. These eruptions altered climates temporarily, cooling them with ash clouds or warming them with greenhouse gases. Some volcanic events may have driven smaller extinctions, reshaping ecosystems and clearing the way for new groups to rise. In the long run, they were part of the same tectonic forces that built mountains and split continents. Another reminder that life and Earth are inseparable. To imagine the Mesozoic world is not just to picture dinosaurs in forests, but to see a planet where nothing stood still. A map of the Triassic looks nothing like a map of the late Cretaceous. Continents that were once joined as Pangaea were scattered. Oceans that were once closed had opened, and mountains had risen in places that had once been flat. Every creature we've spoken of lived against this backdrop, their fate tied to the slow dance of continents. And in this way, the story of life and the story of Earth are the same. Dinosaurs thrived not just because of their anatomy, but because the world shifted beneath their feet, creating new habitats, isolating populations, opening opportunities. Marine reptiles filled seas that did not exist before the continent split. Birds arose in forests shaped by changing climates. Even the plants from cycads to flowering species spread and diversified in landscapes molded by mountains and coastlines. The Mesozoic was an age of living change, not just in its creatures, but in the very shape of the planet. To walk across it then would have been to cross continents still drifting apart, mountains still rising, seas still flooding inland. It was an Earth in motion, and that motion wrote the stage for everything that lived upon it. When we think of the Mesozoic, it's easy to picture a calm world of forests and herds, giant dinosaurs moving steadily across open plains, pterosaurs drifting on warm currents, seas filled with reptilian giants. But underneath that image lies another truth. The Earth then, as now, was never still. Volcanoes erupted with violence. Storms swept across seas and coasts. Earthquakes shook the ground, and climates shifted abruptly. For every long stretch of stability that allowed life to flourish, there were moments when the planet reminded its inhabitants of its power. The creatures of the age had to survive not only each other, but also the planet itself. A restless stage that could change the rules without warning. The Mesozoic began in the shadow of one of the greatest catastrophes Earth had ever known, the Permian extinction. Volcanic activity, on a scale difficult to imagine, had poured out immense lava flows across Siberia, releasing gases that poisoned air and water, altering climate and devastating ecosystems. Though that event belonged to the Permian, its echoes carried into the Triassic, where life struggled to recover. Volcanism never ceased, and through the Triassic, Jurassic, and Cretaceous, eruptions reshaped landscapes, added new land, and influenced climate again and again. When continents began to split apart, it was not a quiet process. As the great supercontinent of Pangaea rifted, magma surged upward, creating new crust and vast volcanic provinces. One of the most significant of these came at the end of the Triassic, when massive volcanic eruptions released enough carbon dioxide and other gases to drive climate shifts that contributed to an extinction event. These eruptions, part of what is now called the Central Atlantic Magmatic Province, left behind thick basalt layers spread across multiple continents. For the creatures alive, then the sky would have darkened with ash, rivers would have run with volcanic debris, and ecosystems would have been disrupted for thousands of years. But volcanoes were not only destructive, they also created new habitats, fresh lava fields weathered into fertile soils that supported new plant growth. Mountain ranges formed by volcanic, uplift-shaped rainfall and created new ecological niches. Volcanic islands emerged in the seas, offering fresh environments for life to colonize. Over the long span of the Mesozoic, eruptions were both destroyers and builders, agents of both extinction and renewal. Alongside fire from the earth came tempest from the skies. The Mesozoic climate was often warmer than today's, with high sea levels and broad shallow seas covering continents. These conditions fueled intense storms. Inland seas like the Western Interior Seaway in North America would have been prone to powerful hurricanes, sweeping across vast stretches of shallow water and pounding coastal plains. Imagine herds of hadrosaurs grazing near a shoreline when wind suddenly rose, waves crashing inland, uprooting trees and flooding lowlands. Fossil evidence of storm deposits, layers of sand and debris swept inland, tells us these events happened repeatedly. For the animals that lived there, storms were as real a threat as predators. Storms also influenced life more subtly. Seasonal rains fed rivers and wetlands, supporting lush vegetation that sustained herbivores. Dry seasons forced migrations, driving herds across plains in search of water. Floods reshaped valleys, depositing fertile soils, but also sweeping away plants and animals. Lightning sparked fires that burned through forests, clearing space for new growth. The weather was not background, but an active force, shaping where animals could live and how they behaved. The Mesozoic atmosphere itself was different. Carbon dioxide levels were often higher, warming the climate and fueling vigorous weather systems. This warmth created strong temperature gradients between land and sea, driving winds and storms. In polar regions, long periods of darkness alternated with long periods of daylight, creating unique seasonal patterns. Even there, evidence suggests forests grew, watered by heavy rains and moderated by the greenhouse climate. For the animals that lived through it, life meant adjusting constantly to the rhythms of weather, from storms that arrived without warning to seasons that stretched differently than ours. Earthquakes were another reminder of the planet's restlessness. As tectonic plates shifted and continents split apart, faults slipped and rumbled. For animals, an earthquake meant the sudden shattering of a familiar landscape. Riverbeds shifted, cliffs crumbled, and sometimes whole habitats were transformed. Though the evidence of earthquakes is less direct than volcanic rocks or storm deposits, the tectonic activity that shaped the Mesozoic world guarantees that they were a regular feature. Life on unstable ground had to adapt to a world that could tremble and break without notice. Some of the most dramatic volcanic episodes of the Mesozoic came later in the Cretaceous. Toward its end, immense eruptions in what is now India poured out the Deccan Traps, one of the largest volcanic provinces in Earth's history. Lava spread across vast areas, gases filled the skies, and the climate shifted rapidly. Some scientists argue these eruptions played a role in the mass extinction that closed the Mesozoic alongside the asteroid impact that struck later. Whether as accomplice or cause, the Deccan Traps were another reminder of how profoundly volcanic activity could affect the planet. To imagine living through these events is to place oneself in a world always unsettled. A herd of ceratopsians might graze peacefully one year, only to see ash begin to fall the next, coating leaves and choking rivers. A population of marine reptiles might thrive in a seaway, only for currents to shift as continents moved, changing the availability of food. A forest might grow lush in fertile volcanic soil, then be flattened by a storm in a single night. For every long period of stability, there were disruptions that forced adaptation or ended lives. Yet, life endured. Just as animals adapted to predators, they adapted to the planet's unpredictability. Some developed migratory habits, moving seasonally to follow resources. Others diversified diets, eating a wider range of plants or prey to survive when one food source failed. Plants spread quickly into disturbed areas, exploiting volcanic soils or storm-cleared ground. In this constant negotiation with a restless Earth, resilience became as important as strength. The fossil record preserves glimpses of these struggles. Ash layers trap the remains of plants and animals, recording sudden disasters. Storm deposits in tomb shells and bones swept together by waves. Layers of volcanic rock mark periods of intense eruption, while changes in isotopes track shifts in climate, driven by volcanic gases. Each layer tells of a moment when the Earth itself intervened in the lives of its inhabitants. The image of the Mesozoic as a stable paradise of dinosaurs, is in truth incomplete. It was a world of beauty and abundance, but also of upheaval. Volcanoes poured fire, storms lashed coasts, earthquakes shook plains, and climate swung between extremes. The creatures that thrived were not only those that grew large or fierce, but those that could endure change, adjust to disruption, and survive the restlessness of the earth. And so when we think of that age, we must remember not only the animals and plants, but the forces of the planet itself, always shifting beneath them, always shaping the possibilities of life. The Earth was not a passive stage, but an active participant, sometimes gentle, sometimes violent, but always in motion. The Mesozoic was not only the age of reptiles, it was the age of a restless Earth, and everything alive then carried its imprint. When we think about dinosaurs, we often imagine them as solitary giants, moving across vast landscapes, each creature a figure of strength on its own. But the evidence left behind in stone tells a more complicated and more intriguing story. Dinosaurs were not simply individuals scattered across ancient plains. They lived together. They traveled together. They raised young. They interacted with one another in ways that shaped their survival. The Mesozoic world was not only about claws and teeth or size and speed, but also about connections, relationships, and patterns of life that stretched beyond the single animal. The most striking clues about this come not from bones, but from tracks. Fossilized footprints preserved in mud that hardened into stone reveal patterns of movement that skeletons alone cannot. In places around the world, trackways stretch for meters or even kilometers, left by herds of animals moving together. Some sites show dozens of parallel tracks, all heading in the same direction, the spacing between them consistent, the size of the prints ranging from juveniles to adults. These are not random wanderings. They're signs of coordinated groups of herds moving as one. Imagine standing at the edge of a Triassic or Jurassic floodplain, the ground soft from seasonal rains. A herd of aviarous dinosaurs, perhaps early ceradomorphs, passes by. Adults stride steadily, their legs making deep impressions in the mud. Beside them, smaller footprints of juveniles appear, shorter strides keeping pace with the group. As time passes, the sun dries the ground, the prints harden, and eventually layers of sediment bury them, preserving a moment of movement that will survive for hundreds of millions of years. What we see in those tracks today is not just that dinosaurs walked, but that they walked together. Herring offered clear advantages for herbivores. Traveling in groups provided protection from predators. A lone hadrosaur or sauropod calf would have been vulnerable, but within a herd, the presence of many adults reduced the risk. Larger animals could shield the smaller ones, while sheer numbers discouraged attackers. For predators, group behavior may have helped coordinate hunts, though the evidence for pack hunting is more debated. Still, the possibility that some carnivores cooperated adds another layer to the social complexity of the time. Nesting sites provide even more direct evidence of social lives. In regions from Mongolia to North America, paleontologists have uncovered fossilized nests containing eggs arranged carefully, often in circular patterns. Some sites preserve multiple nests close together, suggesting colonies where many individuals laid eggs in the same area. This behavior mirrors that of modern birds, where communal nesting provides both safety and big numbers and shared vigilance against threats. For dinosaurs, gathering to nest may have been an annual event, bringing herds together in great numbers as they returned to favored sites, season after season. Some nests preserve not only eggs but embryos inside them, frozen in development. Others show hatchlings, tiny dinosaurs that had broken free of their shells only to be buried by sudden floods or storms. These finds raise questions about parental care. Did adults guard the nests? Did they bring food to the young? Some fossils suggest they might have. The famous example of Maiasaura, whose name means good mother lizard, comes from discoveries of nesting colonies with evidence that hatchlings stayed in the nest for some time, their bones showing growth that could not have occurred if they had left immediately. Adults may have fed or protected them until they were strong enough to survive alone. Other dinosaurs may have been more independent, laying eggs and moving on, leaving the hatchlings to fend for themselves. The diversity of strategies likely matched the diversity of dinosaurs themselves, with some providing care and others not, much as we see among reptiles and birds today. But the very presence of nesting colonies shows that at least some species interacted closely during reproduction, returning together to specific sites, creating generations of fossils in the same places. Tracks and nests together reveal the rhythms of dinosaur life. Herds moved across landscapes, leaving parallel prints. They gathered in nesting grounds, leaving clusters of eggs. These behaviors point to memory, communication, and coordination. Dinosaurs were not only products of their anatomy, but of their interactions, shaped by the benefits and challenges of living in groups. Predators left their traces too. Trackways of theropods, the bipedal carnivores sometimes show multiple individuals moving together. Whether this represents true cooperation or simply coincidence is debated, but the possibility of pack behavior cannot be dismissed. Fossils of Allosaurus and other large predators are often found in groups, though whether these represent social living or individuals drawn together by food is uncertain. Still, the potential that some carnivores coordinated their actions adds to the sense that dinosaur societies were varied and dynamic. Fossil bone beds provide further evidence. In some sites, the remains of dozens or even hundreds of individuals are preserved together, suggesting herds that died in floods, droughts, or volcanic events. While some may represent chance gatherings, others point to the reality that these animals lived and moved in groups. A mass death site of ceratopsians, for instance, reflects the fate of a herd caught in a sudden catastrophe. From such sites, we glimpse not just individuals, but entire communities. The social lives of dinosaurs also extended to displays and communication. Frills, crests, horns, and other features may not have been only for defense or combat, but for signaling. A herd of hadrosaurs with crested heads may have produced resonant calls echoing across valleys to coordinate movement or attract mates. Ceratopsians with elaborate frills may have used them to identify individuals, strengthen bonds, or intimidate rivals. These physical features suggest a world where visual and auditory communication played major roles, where life in groups required more than just presence, but recognition and interaction. The behavior of nesting, herring, and communication reveals that intelligence was not limited to survival instincts. Coordination, memory of nesting sites, care for young, and recognition of companions all point toward cognitive abilities. Dinosaurs were not mindless giants, but animals with behavior suited to complex lives. Just as modern birds demonstrate intelligence in their social lives, dinosaurs may have shown capacities that extended beyond simple survival. Even solitary species were influenced by these patterns. A predator that hunted herd animals needed to adapt strategies for targeting individuals. A solitary herbivore still needed to avoid large herds that could defend themselves. The structure of ecosystems was shaped by the presence of group living, by the interplay between herds and hunters, by the annual cycles of nesting and migration. Storms, floods, and volcanoes often captured these lives suddenly, preserving them in a moments of tragedy. A herd caught in a flood, swept together and buried in sediments, left behind a fossil bed that reveals their social bonds. A nesting colony, overwhelmed by ash, preserved the tender evidence of eggs and hatchlings. These moments are windows into behavior, records of life interrupted, but also of life shared. To walk among dinosaurs in their time would not have meant seeing one or two scattered across a horizon, but hearing the movement of herds, the calls of adults to young, the stamping of feet across plains. It would have meant finding nesting grounds crowded with individuals, the air filled with noise and activity. It would have meant predators lurking at the edges, watching for a chance, while groups of herbivores stood together for protection. The Mesozoic landscape was alive, not only with bodies but with communities. And so when we imagine dinosaurs, we must picture not just isolated creatures but networks of life bound together in patterns of movement and care. The fossil record, in its silent tracks and buried nests, speaks to those connections, reminding us that these animals were part of societies as real as any we see among modern herring mammals or colonial birds. The age of dinosaurs was an age of individuals, but also of herds, families, and communities living together on a restless planet. For more than 100 million years, the landscapes of the Mesozoic were green, but different from the ones we know today. Forests were filled with conifers, cycad, ginkgos, and ferns. These plants reproduced with spores or cones, spreading slowly, relying on wind or water to carry pollen. The air was filled with the smell of resin rather than blossoms, the ground shaded by palm-like fronds and towering conifer branches. Herbivorous dinosaurs fed on these plants, tearing needles and leaves, chewing cyc, stripping ferns. It was a world of abundance, but also of limitation. And then, in the Cretaceous, something new appeared. At first it was subtle, scattered among the older vegetation, small plants with structures no larks I had seen before. They had petals, colors, and scents. They did not rely only on the wind, but invited animals into their reproduction. These were the first flowering plants, the angioperms, and though they arrived quietly, their impact on life would be profound. Fossil evidence suggests the earliest angioperms may have appeared in the early Cretaceous, perhaps even earlier. They were not immediately dominant. In fact, they were rare at first. Just one more experiment in evolution's vast portfolio. But what set them apart was the efficiency and flexibility of their reproduction. Flowers allowed precise transfer of pollen, often aided by insects. Seeds were enclosed in fruits, protected, and often carried far by animals that ate them. This combination gave flowering plants a competitive edge, letting them spread quickly and adapt to a wide range of environments. The relationship between flowers and insects was especially significant. Insects like beetles and flies had been around long before angioperms, feeding on other plants or detritus. With the arrival of flowers, new partnerships formed. Pollinators gained food in the form of nectar or pollen, and in return, they carried pollen from plant to plant. Over time, this interaction grew more complex, with insects evolving specialized bodies to gather nectar or pollen efficiently, and plants evolving shapes and colors to attract specific insects. Bees, butterflies, and many other groups would eventually flourish through these connections, though their full diversity came later. Even in the Cretaceous, though, the beginnings of these mutual relationships were reshaping ecosystems. For dinosaurs, the impact of flowering plants was more gradual, but no less important. Herbivores that once fed on conifers and cycads found new options in flowering shrubs and conifer trees. The leaves of angioperms are often softer and more nutritious than the tough needles of conifers, making them attractive food sources. As flowering plants spread, they likely supported larger populations of herbivores, which in turn supported predators. Some scientists argue that the rise of angioperms may have fueled the success of certain groups of dinosaurs, providing the food base for vast herds of hadrosaurs and ceratopsians that dominated the late Cretaceous. The landscapes themselves were transformed. In earlier Mesozoic forests, the canopy was dominated by tall conifers with open understories. With flowering plants, new layers of vegetation appeared. Shrubs, vines, and small trees filled spaces between larger trees, creating more complex habitats. This structural diversity offered niches for more kinds of animals, from insects to small vertebrates, and may have influenced the evolution of new forms of behavior. Dinosaurs moving through these environments would have encountered denser foliage, more varied plant life, and seasonal patterns driven by flowering and fruiting. Flowers also changed the chemistry of the air and soil. Their rapid growth and high productivity altered nutrient cycles, affecting everything from soil microbes to atmospheric gases. By creating fruits and seeds that animals carried and deposited, angiosperms reshaped the distribution of organic matter. They accelerated ecological processes, increasing the energy available in ecosystems. One striking aspect of the flowering plant revolution is how quickly they spread once they gained a foothold. In the fossil record, their presence jumps from scattered traces to dominance within tens of millions of years, a relatively short span in geological terms. By the late Cretaceous, angiosperms were widespread, growing alongside older plant groups, but increasingly displacing them in many environments. Fields of flowering plants, forests with broadleaf trees, and vines creeping through canopies became common sights. This shift had cascading effects. Insects diversified in response to the opportunities offered by flowers. Birds descended from theropod dinosaurs may have found new food sources in fruits and seeds. Small mammals, still minor players in the Mesozoic, also took advantage of these resources, feeding on fruits and dispersing seeds in return. The rise of angiosperms laid the groundwork for the ecosystems that would dominate after the dinosaurs' extinction, shaping the future long before that event arrived. The fossil evidence of Cretaceous flowers is delicate but revealing. Tiny pollen grains, preserved in sediments, show the diversity of angiosperms increasing rapidly. Fossilized leaves with distinctive vein patterns trace their spread across continents. In some rare cases, flowers themselves have been preserved, their structures still visible under microscopes after millions of years. Amber, fossilized tree resin, has captured insects dusted with pollen, frozen in the act of visiting blooms. These finds provide direct evidence of the new relationships forming between plants and animals. Moments of ecological innovation caught forever in golden droplets. The arrival of flowering plants also meant the arrival of color in new forms. While earlier plants were mostly green, flowers brought reds, yellows, purples, and whites. To the human imagination, it's tempting to see a Cretaceous meadow dotted with blossoms, insects flitting between them, dinosaurs grazing nearby. While the scale of blooms may not have matched modern meadows, the principle was the same. Flowers used color and scent to attract partners in reproduction, making the landscape more varied and visually striking. For animals with color vision, like many insects and possibly some dinosaurs, this would have been a sensory shift as well as an ecological one. Not all changes were beneficial to every group. Some older plant lineages declined as flowering plants expanded. Cycads, once dominant, retreated to smaller ecological niches. Ginkgos, more diverse in the Mesozoic, dwindled to a single species that survives today. Conifers remained important, especially in cooler or harsher environments, but their relative dominance decreased. The rise of angiosperms did not erase older plants, but altered the balance of power in ecosystems in pushing some aside while creating new opportunities for others. It is worth considering how this quiet revolution might have looked from the perspective of a lick dinosaur. For a hadrosaur moving through a forest, the spread of angiosperms meant softer leaves, more abundant food, perhaps seasonal fruits. For a ceratopsian, it meant grazing in mixed environments, some dominated by broadleaf plants, others still by conifers. For predators, it meant more prey, supported by richer vegetation. Over time, these changes may have shifted migration patterns, herd sizes, and even the strategies of survival. The influence of flowering plants extended beyond the Cretaceous. After the extinction that ended the age of dinosaurs, angiosperms became the foundation of modern ecosystems, supporting the diversification of mammals, birds, and insects. But their origins trace back to that moment in the Cretaceous, when petals first unfolded, and the pollen first traveled with the help of wings and legs. Without that event, the world we know would not exist in its present form. The Cretaceous bloom was not a sudden explosion, but a steady spread, a transformation that unfolded step by step across millions of years. Yet its impact was as great as any dramatic extinction or evolutionary leap. By inviting animals into their lives by offering nectar, fruit, and shelter, flowering plants changed the rules of the game. They rewrote the interactions between plants, and animals set the stage for new lineages to thrive, and filled the world with colors and scents unknown before. To walk through a Cretaceous landscape after the rise of angiosperms would have been to walk in a world both ancient and surprisingly familiar. You would see conifers still standing tall, cycads with their stiff fronds, but also broadleaf trees, flowering shrubs, and fruits hanging where once there had been only cones. You would hear insects buzzing, some carrying pollen from bloom to bloom. You would watch a dinosaur pause to strip leaves from a branch heavy with flowers scattering, petals to the ground. In those small moments, the transformation was visible, the beginning of a world that would outlast the giants themselves. The arrival of flowers was one of evolution's most powerful innovations. It was not loud like the roar of a predator, nor sudden like the strike of an asteroid. It was patient, persistent, and irresistible. By the end of the Cretaceous, flowers had secured their place, reshaping the surface of the Earth and ensuring that when the age of dinosaurs ended, the stage was set for a new chapter in life's story. To picture an entire era stretching over 180 million years is difficult, but to picture a single day is different. A day brings it closer, shrinking vast time into a cycle we know well. The sun rises, life stirs, the world moves through its patterns, and then night falls. If you could stand in the Mesozoic, anywhere from the Triassic to the Cretaceous, you would find that the rhythm of day and night carried just as much meaning as it does today. Each dawn began a new round of survival, of feeding, of moving, of resting. Dinosaurs, reptiles, insects, and plants all responded to the steady march of light and darkness, and from these responses came the fabric of their lives. The sun at dawn would have warmed the land quickly. In many places, the Mesozoic climate was warmer than what we know today, with higher carbon dioxide levels and fewer extremes of freezing cold outside the poles. As the light spread across plains, forests, and seas, animals would stir. Herds of herbivores may have risen from where they had rested, their breath visible in the coolness of the early morning, beginning to graze before the heat of midday. Small, feathered dinosaurs might have fluttered down from perches in trees, calling to one another with chirps and croakies, the first sounds of the day. Insects would emerge as the temperature rose, buzzing between plants, feeding on pollen, or beginning their search for food. Near rivers and lakes, the surface might break with the movement of aquatic reptiles, a plesiosaur lifting its head above the water, a school of fish scattering, turtles clambering to warm themselves on a muddy bank. The shorelines of the Mesozoic were alive with activity from the very first hours of sunlight. Just as today, we see wetlands come alive with birds and mammals at dawn. For many herbivorous dinosaurs, mornings were the safest time to feed. In cooler air, with long shadows stretching across open land, predators might still be sluggish, conserving energy for the hunt. Later, a group of hydrosaurs, duck-billed dinosaurs, might move in loose formation, heads bobbing as they cropped vegetation. Their young would stay close, nudged by adults, while others scan the distance for movement. The sound of chewing, the rustle of plants, the steady of feet across damp soil would have filled the early light. In forests, smaller creatures scurried through undergrowth. Mammals, mostly small and nocturnal, sometimes extended their activity into the early morning, foraging for seeds, insects, and fruits before retreating to safety. Feathered theropods move quickly through branches, some leaping short distances from tree to tree, hunting insects or small reptiles. Crocodile-like arosaurs slipped quietly through water channels, waiting for an unwary animal to approach for a drink. The cycle of predator and prey was constant. Each day, beginning with both sides adjusting their chances, by midday, the sun would have been high and strong. Temperatures in many regions of the Mesozoic could rise sharply, pushing animals to seek shade or water. Large sauropods towering above the canopy may have continued to feed through the heat, stripping branches with little concern for temperature, their size insulating them from many discomforts. But smaller dinosaurs likely rested, taking shelter in shade until conditions were easier. Around waterholes, animals would gather, drinking cautiously while keeping watch for predators. This was also the time when storms could suddenly build. The warm climate of the Cretaceous especially created conditions for intense rainfall and dramatic weather. A morning of heat could transform into an afternoon of thunder, sheets of rain pelting the ground, rivers swelling with sudden runoff. For animals, this meant both danger and relief. Danger from floods or slippery terrain, relief from the heat and dryness. A herd, caught in a storm, would cluster together, adults circling young, waiting for the violence to pass. Forests would drip with water long after, releasing scents of wet leaves and resin. Afternoons brought a different rhythm, with the air cooler after storms, or the sun lowering toward the horizon. Activity returned. Predators often hunted at these hours, conserving energy for when prey was more vulnerable. A theropod, like Allosaurus, or later Tyrannosaurus, might have stalked herds, waiting for one individual to lag behind. Smaller predators darted after lizards or mammals. In the seas, mosasaurs or ichthyosaurs might have surged upward after schools of fish, their movements breaking the surface in splashes that echoed in the still air. Evening light would have transformed the landscape into something quieter. Herds settled into safe areas, mothers guiding young into the center, adults standing guard on the edges, calls carried over long distances, low rumbling sounds between sauropods, honks and cries between hadrosaurs. Insects hummed in thick clouds, drawn to the cooling air. Pterosaurs glided low, perhaps feeding on swarms of insects over rivers. In forests, the shadows deepened, and nocturnal life began to stir. Night in the Mesozoic was a world of its own. With fewer artificial lights and a clearer atmosphere, the stars would have been bright, the Milky Way stretching in dense bands across the sky. The moon, waxing or waning, cast pale light across forests and plains. For many creatures, this was the time to emerge. Mammals scurried under cover of darkness, safer from large predators. Some small dinosaurs, feathered and bird-like, may have been nocturnal as well. Their eyes adapted to dim light. Owls had not yet evolved, but insect-hunting dinosaurs may have filled similar roles, starting silently after prey. Larger predators also moved at night. The cover of darkness allowed them to approach more closely. Their senses adapted to detect sound and movement. A ceratopsin herd sleeping together might have been vulnerable if a predator managed to isolate a young one. Yet, the herd structure itself was a defense. The presence of many individuals, discouraging even the boldest hunters. Nighttime meant risk, but also the cycle of rest, each creature relying on instinct and adaptation to survive until morning. Across different parts of the world, these rhythms played out differently. In polar regions, long days or nights stretch the pattern, forcing animals to adapt to extended periods of light or darkness. In equatorial zones, the cycle was more consistent with regular alternations of day and night and frequent storms. Each ecosystem had its own version of the daily story, but all were tied to the same solar rhythm that governs life today. The ordinary day in the Mesozoic was filled with moments of calm, punctuated by bursts of drama. Feeding, moving, resting, and avoiding predators formed the baseline. But sudden storms, shifting winds, or the arrival of a predator could change everything in an instant. Over millions of years, these cycles repeated generation after generation, shaping behavior, instincts, and evolution itself. The fossil record captures flashes of this daily life. A nest buried in ash, tracks frozen mid-stride, a herd entombed by flood sediments. Each of these is a snapshot of an ordinary day that became extraordinary through preservation. It's easy to focus on the grand events, the extinctions, the rises of new groups, the geological upheavals. But most of the Mesozoic was live, not in those rare moments, but in the steady pace of days like these. Dinosaurs fed, rested, raised young, and moved with the rhythms of the sun. Plants grew, flowered, and seeded. Insects buzzed and crawled. The extraordinary age was built out of ordinary days, each one a thread in the fabric of deep time. If you could stand quietly in that world and watch a single day pass, you would see animals interacting, landscapes shifting in light and shadow, the continuity of life echoing across millions of years. It would feel both alien and familiar, strange creatures in unfamiliar forms, but patterns of behavior we still recognize in the animals around us today. The Mesozoic was vast, but within it, each sunrise and sunset mattered. Each ordinary day carried the survival of countless lives forward into the next. For most of the Cretaceous, life seemed unshakable, but herds of ceratopsians roamed North America, hadrosaurs filled the river valleys, sauropods still held their ground in the southern hemisphere, and predators like Tyrannosaurus and Allosaurus dominated the hunt. The seas teemed with mosasaurs and plesiosaurs. The skies belonged to pterosaurs, and the first true birds and flowering plants had spread into every corner of the land. It was a flourishing world balanced between predator and prey, plant and consumer, sea and land. Yet beneath that appearance of stability, forces were already gathering that would change everything. Toward the end of the Cretaceous, volcanic eruptions in what is now India poured out vast flows of lava, known as the Deccan Traps. These eruptions released gases, including carbon dioxide and sulfur dioxide, into the atmosphere. Over thousands of years, they altered climate, sometimes warming it with greenhouse gases, sometimes cooling it as aerosols reflected sunlight. Ecosystems felt these shifts, but life adapted as it always had during the Mesozoic. Still, the world was already unsettled even before the final blow arrived. That blow came about 66 million years ago, when an asteroid roughly 10 kilometers wide struck near the Yucatan Peninsula in present-day Mexico. In an instant, unimaginable energy was released. The impact blasted a crater more than 180 kilometers across, through vast amounts of rock and dust, into the sky, and generated shockwaves that spread across the globe. Within hours, tsunamis surged across coastlines. Forests near the impact were flattened or set ablaze, and the sky itself began to change. Fires spread, not only from the initial explosion, but also from debris re-entering the atmosphere. As ejecta rained down, the friction heated the air, igniting global wildfires. Charcoal deposits in sediments from this time record the scale of the burning, evidence that entire landscapes were engulfed. For the animals and plants alive at that moment, survival was not just a matter of avoiding predators or finding food, but of escaping fire and smoke that spread across continents. In the days and weeks after the impact, the skies darkened. Dust, ash, and aerosols filled the atmosphere, blocking sunlight. Photosynthesis faltered as plants were deprived of light, and with it, the foundation of food chains began to collapse. Herbivores lost their food, predators lost their prey, and ecosystems unraveled. This period of darkness, sometimes described as an impact winter, may have lasted months or even years, plunging the planet into cold as sunlight failed to warm the surface. Temperatures dropped sharply, challenging species already stressed by fire and famine. The seas also bore the weight of disaster. Tsunamis reshaped coastlines, but the longer-lasting effect came from changes in chemistry. As dust and sulfur entered the atmosphere, acid rain fell into oceans, altering their balance. Combined with falling temperatures, these changes disrupted marine ecosystems. Plankton, the base of marine food chains, struggled, and without them, so larger creatures followed. The once abundant mosasaurs, plesiosaurs, and ammonites could not endure these shifts, vanishing along with many other marine groups. On land, the effects were no less devastating. Forests burned, leaving charred remnants. With sunlight dimmed, new growth was slow, and herbivores found little to eat. Small animals that could subsist on seeds or detritus fared better, while large herbivores like hadrosaurs and ceratops faced starvation. Carnivores that depended on them soon followed. The mighty Tyrannosaurus, apex predator of its time, fell with its prey, leaving behind no direct descendants. Yet not everything perished. Crocodiles, able to survive long periods without food and living in aquatic habitats, endured. Birds, descendants of small theropod dinosaurs, found ways to persist, perhaps feeding on seeds or insects that survived in the soil. Mammals, small and adaptable, took advantage of niches left vacant by the collapse of larger animals. Insects, fungi, and plants with hardy seeds or spores also survived, waiting out the long darkness until conditions improved. The extinction at the end of the Cretaceous was selective, but its impact was enormous. Roughly 3/4 of all species on Earth disappeared, including all non-avian dinosaurs, most marine reptiles, and countless other groups. The Mesozoic ended not with a slow decline, but with a sudden catastrophe that reshaped the planet. When sunlight finally returned and ecosystems began to rebuild, the world that emerged was different, set on a new trajectory. The evidence of this event is preserved across the globe. A thin layer of clay, rich in the element iridium, marks the boundary between the Cretaceous and the Paleogene. Iridium is rare on Earth's surface, but common in asteroids, a fingerprint of the impact. This layer, found on every continent, is the record of the dust that settled after the skies cleared. Fossils below the layer tell of the Mesozoic's abundance, while above it lies the record of a new world. With dinosaurs gone and mammals and birds rising in their place, for paleontologists, this boundary is one of the most striking lines in the history of life. It is not just a marker of extinction, but a marker of transformation. Without the asteroid, dinosaurs might have continued to dominate for millions of years longer. Mammals, still small and marginal in the late Cretaceous, may never have had the chance to rise. Human history itself is tied to this moment, a distant consequence of that single day of impact. To imagine the event is to imagine chaos on a scale almost beyond comprehension. A bright streak in the sky, a deafening impact, shockwaves flattening everything for hundreds of kilometers, tsunamis rising higher than any waves in memory, forests igniting spontaneously, skies darkening until day turned to twilight, temperatures dropping until even the strongest animals faltered. And yet, amidst that devastation, life endured in small, tenacious forms, carrying forward into a new age. The great ending of the Mesozoic was not only an end, but also a beginning. In the aftermath, as ecosystems rebuilt, mammals diversified, birds spread, and flowering plants continued their expansion. The Cenozoic dawned from the ashes of the Cretaceous, a new chapter shaped by the survivors of extinction. The world of today, with its diversity of mammals, birds, and angiosperms, is the legacy of that transformation. And so when we think of the Mesozoic, we must hold in mind not only its long ages of dinosaurs and seas of reptiles, but also its sudden and violent close. Fire, darkness, and extinction brought down the giants. But from that upheaval came a new world, one that would eventually give rise to us. The story did not end with the asteroid. It turned, and life moved on, carrying the imprint of that catastrophe into every species that followed. When we walk through the world today, it is easy to think of the Mesozoic as gone, a vanished chapter buried beneath rock and time. The dinosaurs are no longer striding across plains. The seas are no longer ruled by mosasaurs or ichthyosaurs. The skies are no longer filled with giant pterosaurs. And yet, when we look more closely, the echoes of that age surround us in ways both visible and hidden. The line between then and now is not as sharp as we sometimes imagine, and the legacy of the Mesozoic continues to shape the world we inhabit. The most obvious connection is with birds. Every pigeon on a city street, every crow perched on a wire, every hawk soaring above farmland is a descendant of theropod dinosaurs. Their hollow bones, their feathers, their eggs, all trace back to their ancestors in the Jurassic and Cretaceous. When you hear the song of a sparrow at dawn, you're hearing the distant voice of creatures that shared their world with Triceratops and Ankylosaurus. The very act of flight, so effortless in a gull skimming the surf or a swallow darting after insects, is a living continuation of experiments in the skies that began with pterosaurs and early birds. The dinosaurs did not truly vanish. They adapted into forms that continue to thrive, filling every continent and nearly every environment. Plants also carry that legacy. The flowering plants that dominate our forests, gardens, and farmlands are the descendants of the quiet revolution of the Cretaceous bloom. Every fruit we eat, every field of wheat or rice or corn, every oak and maple tree is part of the lineage that began when petals first unfolded and insects first carried pollen from bloom to bloom. The world we see with its colors and scents, its diversity of fruits and seeds, is the direct continuation of changes that took root among dinosaurs. When we step into an orchard, smell a rose, or watch bees moving from flower to flower, we are living among the creations of that time. Even the shapes of continents and oceans we know today were sculpted during the Mesozoic. The breakup of Pangaea, the drifting of land masses, the opening of the Atlantic, these movements set the stage for the geography of the present. The mountains that rise across continents, the coastlines where we live and trade, the arrangements of habitats that guide climate and migration, all began to take their modern form in that age. Every map of Earth reflects not only the present, but also decisions written in stone millions of years ago, when plates shifted and oceans spread. Our own existence is tied in unexpected ways to the catastrophe that ended the Mesozoic. Without the asteroid impact, mammals might have remained small, overshadowed by dinosaurs for millions more years. Instead, their survival through that crisis opened paths for them to diversify, to expand into new roles, to eventually give rise to primates, and much later, to humans. The end of the Mesozoic was not just an end for dinosaurs, it was the beginning of a story that led to us. In that sense, every human walking today is part of the legacy of that event, a living echo of the survival that carried life into the Cenozoic. The fossils themselves are echoes, silent but powerful. When we find a skeleton preserved in stone, we are seeing not just bones, but a memory of a life lived. A trackway frozen in mud records the steps of a herd across a floodplain. A nest of eggs captures the moment of reproduction, an attempt to carry life forward into the next generation. Each fossil is a message across time, an imprint of existence that continues to speak long after the creatures themselves are gone. Museums are filled with these voices, and every time we look at them, we connect across an almost unimaginable span of time. But the echoes are not only physical, they're also cultural. Dinosaurs live in our imagination in ways few other extinct creatures do. From childhood toys to films, from books to television, they have become symbols of both power and fragility. We see them as unstoppable giants, yet we also know they perished in an instant of cosmic chance. They remind us of the strength of life, but also of its vulnerability. This duality makes them resonate with us deeply as we measure our own place in the story of Earth. There is something profoundly humbling in realizing that the ground beneath our feet holds these memories. Every layer of rock is a page of history, and within those pages are the remains of forests, seas, and creatures that lived long before us. The Mesozoic is not only a time of fascination for paleontologists, it is part of the foundation of our world, one that continues to inform the shape of life and the structure of our ecosystems. By studying it, we we learn not only about dinosaurs, but about resilience, adaptation, and the cycles of change that govern the planet. When we consider climate change, the echoes of the Mesozoic remind us of what happens when conditions shift. The warmth of that era, the rise and fall of sea levels, the impact of volcanism, and finally, the sudden catastrophe of an asteroid, all teach us that life responds to change, sometimes adapting, sometimes failing. The extinction that closed the Mesozoic warns us that stability can be fragile, that ecosystems can collapse quickly under stress. In these echoes, there are lessons not only about the past, but about our future. There is also continuity in the smaller details, the way birds preen their feathers, the way crocodiles slip silently through water, the way lizards bask in the sun. All are behaviors that existed in some form in the Mesozoic. They are everyday actions that link across time, connecting us to creatures we will never see alive but can still understand. In this way, the Mesozoic has never truly ended. It continues through the survival of lineages, the persistence of behaviors, and the enduring shape of ecosystems. The echoes reach even further into the human imagination of time itself. To think in terms of millions of years stretches our perspective beyond the scale of our daily lives. It forces us to see that we are part of something vast, a continuity that includes creatures long gone. The Mesozoic teaches us patience, humility, and awe. It reminds us that we are temporary participants in a much longer story, one that began long before us and will continue long after. And so, when we step outside and hear birdsong, when we look at flowers blooming in spring, when we see mountains rising in the distance, or rivers carving their paths, we're surrounded by reminders of that world. The echoes of the Mesozoic are not locked away in stone. They're in the life that thrives today, in the landscapes we cross, in the rhythms of nature. They're in us, too, in the chance survival that gave mammals their opening, in the curiosity that drives us to uncover fossils, in the imagination that carries us back across millions of years to picture what once was. The Mesozoic is gone, but it is not lost. Its traces endure in the living and the non-living, in the visible and the invisible, in the scientific and the cultural. To reflect on it is to see that we are not separate from deep time, but part of it, shaped by it, carrying it within us. Every echo of that age reminds us that life endures, adapts, and transforms, and that we too are only one moment in the ongoing story. And with that, we'll leave our journey here for now. If you've enjoyed wandering through these ancient worlds, you might consider staying with us for more stories about Earth and its deep history. A like or a subscribe helps us keep exploring together, but only if it feels right to you. For now, thank you for listening, and may your own days and nights carry a little of that same wonder the Mesozoic left behind.